The universe looks full. It isn't. Space is 99.99999999999999958% empty, and that emptiness is growing. Right now, at this exact moment, distant galaxies are being pushed past the edge of what we can ever observe. They're not just moving away, they're vanishing forever, crossing a cosmic horizon from which no light, no signal, no evidence of their existence will ever return. In a few trillion years, every galaxy beyond our local neighborhood will be gone. The night sky will go dark, and any civilization looking up from Earth, assuming Earth still exists, will see nothing. No distant stars, no proof the universe was ever bigger than a single cluster of nearby galaxies. They will look out into the void and assume they are alone. They will be wrong, but they'll have no way to know it. We are living in a rare and brief window of cosmic history where the universe is still visible, where we can still see the afterglow of the Big Bang, still map the web of galaxies stretching across billions of light years, still detect the faint fingerprints of everything that came before. But we're also living in the era when scientists finally measured what the universe is actually made of, and the answer is deeply, profoundly unsettling. 5%. That's how much of reality is made of stuff we can see. Atoms, stars, planets, gas, light, everything humans have ever touched or observed. The other 95% is invisible. 27% is dark matter, a gravitational ghost holding galaxies together. 68% is dark energy, a force we don't understand that's tearing space-time apart at an accelerating rate. And the empty space in between, that's not empty either. This is the story of what's really out there and what isn't. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in, this is going to be a good one. Look up at the night sky on a clear evening, far from city lights, and you'll see thousands of stars scattered across the darkness. The Milky Way stretches overhead like a river of light. Planets hang steady among the twinkle. If you have a telescope, you can pull in galaxies, nebula, clusters of ancient suns burning quietly in the void. The universe, from that vantage point, looks full, crowded even. A cosmic city with no empty lots. That feeling is a lie, not a small lie, not a rounding error, a fundamental misrepresentation of what the universe actually is. Because when you run the numbers, when you take every star, every planet, every moon, every asteroid, every speck of dust, every atom of gas drifting between the galaxies, every black hole, every neutron star, every quasar blazing at the edge of the observable cosmos, and you add it all together and measure it against the total volume of space itself, you get a number so lopsided it barely registers as real. The universe is approximately 99.999999999999999999999999999999999999998% empty space. Read that again. 99.999999999999999999998%. That's not a typo. That's not an exaggeration for effect. That is the actual ratio of emptiness to matter when you calculate the average density of the cosmos and compare it to the volume it occupies. You could fit all the matter in the observable universe into a space the size of a grain of sand, and the rest, the overwhelming rest, would be nothing. Void, absence, a silence so complete that calling it empty feels generous, and it gets worse. Because even that tiny fraction of stuff, that microscopic sliver of existence we call matter, is mostly empty too. Atoms themselves are almost entirely hollow. The nucleus sits in the center, absurdly small, and the electrons orbit at distances so relatively vast that if you scaled an atom up to the size of a football stadium, the nucleus would be a marble on the 50-yard line, and the electrons would be gnats buzzing somewhere in the upper deck. The solid chair you're sitting on, the floor beneath your feet, your own body, all of it, is mostly void, held together by forces we can't see, separated by distances we can't perceive. So the universe isn't just mostly empty, it's empty within empty within empty. Emptiness stacked on itself like Russian dolls made of nothing. For most of human history, we didn't know this. We looked up and saw fullness because we were looking with eyes designed to notice light, not absence. The stars were there, bright and obvious. The dark between them seemed like background, like the stage a play is performed on. We catalogued constellations, charted the wandering planets, named the brightest objects we could see, and assumed that what we were seeing was more or less the whole picture. A sky full of lights meant a universe full of things. Then we built better instruments, telescopes that could see farther, cameras that could capture fainter objects, spectrographs that could split light into its component colors and read the chemical fingerprints of distant suns. And the more we looked, the more we found. Galaxies beyond our own, billions of them, then hundreds of billions, then estimates climbing past 1 trillion, each one containing hundreds of billions of stars. The numbers became so large they stopped meaning anything. 1 billion galaxies, 1 trillion stars per galaxy. The mind gives up. The universe, it seemed, was even fuller than we thought. Except it wasn't, because while the telescopes were finding more objects, the physicists were doing something else. They were weighing the universe, not literally, obviously. You can't put the cosmos on a scale, but you can measure how things move. You can watch how galaxies rotate, how they cluster together, how light bends around massive objects. And from those movements, you can calculate how much mass must be present to produce the gravitational effects you're observing. In the early 1900s, astronomers started noticing something strange. Galaxies were rotating in ways that didn't make sense. The outer edges were moving too fast. Stars on the rim of a spiral galaxy should be orbiting more slowly than stars near the center, the same way planets farther from the sun take longer to complete their orbits. That's what Newton's laws predict. That's what should happen if the only mass in a galaxy is the mass you can see in the stars and gas. But the outer stars weren't slowing down. They were moving just as fast as the inner ones, sometimes faster. It was as if something invisible was holding the galaxy together, adding mass that telescopes couldn't detect. For decades, this was treated as a curiosity, a puzzle. Maybe the calculations were wrong. Maybe there was dust we weren't accounting for. Maybe gravity worked differently at galactic scales. Then in the 1970s, an astronomer named Vera Rubin looked at the problem more carefully. She measured the rotation curves of dozens of spiral galaxies, plotting how fast stars were moving at different distances from the galactic center. The data was unambiguous. Every galaxy she looked at was rotating too fast, and the only way to explain it was to assume that each galaxy contained far more mass than anyone could see. Mass that didn't emit light, mass that didn't absorb light, mass that interacted with the universe almost entirely through gravity. Invisible mass, holding galaxies together like scaffolding you can't photograph. They called it dark matter. Not because it's literally dark, but because it doesn't interact with light at all. You can't see it, you can't touch it. You can shine a flashlight through a cloud of it, and the beam won't scatter, won't dim, won't notice the cloud is there. Dark matter doesn't care about photons. It only cares about gravity. And there's a lot of it, a lot. When scientists finally added up how much dark matter would be needed to explain the way galaxies move, the way galaxy clusters hold together, the way light bends around massive structures in space, they arrived at a number that redefined everything. Dark matter outweighs visible matter by a ratio of roughly 5-to-1. For every kilogram of stars, planets, gas and dust in the universe, there are 5 kilograms of dark matter sitting quietly in the background, unseen, undetected, holding the whole structure together. That means visible matter, the stuff we can actually observe with telescopes, the stuff that makes up everything you've ever seen or touched or heard about, accounts for only about 5% of the total mass in the universe. 5%. Everything ever seen. Every star, every planet, every person, every atom in every object across the entire observable cosmos. 5%. That's the first shock. That everything we think of as the universe is actually a rounding error, a thin film on the surface of something much larger and much stranger. But it gets worse, because dark matter isn't the only invisible component. It's not even the biggest one. In 1998, 2 independent teams of astronomers were studying distant supernovae, trying to measure how fast the universe was expanding. They expected to find that the expansion was slowing down. Gravity, after all, pulls everything together. The universe might be flying apart now, but the combined gravitational pull of all the matter in it, visible and dark, should be acting like a brake, gradually slowing the expansion over billions of years. The data said the opposite. The universe wasn't slowing down, it was speeding up. Galaxies weren't just moving away from each other, they were accelerating, flying apart faster and faster as time went on. Something was pushing them, something with enough force to overpower the gravity of every star, every galaxy, every clump of dark matter in the cosmos. They called it dark energy. And unlike dark matter, which at least behaves like matter, clumping together and holding galaxies in place, dark energy is something else entirely. It doesn't clump, it doesn't gather, it fills all of space uniformly. A kind of background pressure that pushes outward everywhere at once. It's not a substance in the traditional sense, it's more like a property of space itself. The more space there is, the more dark energy there is, and the harder it pushes. When scientists calculated how much dark energy would be needed to produce the acceleration they were observing, they got another absurd number. Dark energy accounts for roughly 68% of the total mass energy content of the universe. Not 5%, not 27%, 68%. More than twice as much as dark matter. More than 10 times as much as all the visible matter combined. So here's the inventory. 5% visible matter, 27% dark matter, 68% dark energy. Add it up and you get a universe where 95% of the content is completely invisible, undetectable by any instrument that relies on light, unknown in composition, unexplained in origin. 95% of the universe is missing, or rather, we're the ones who are missing. We're the 5%, the exception, the thin visible skin on an invisible body. Think about what that means for a second. You look up at the night sky and you see stars. You point a telescope into the deepest, darkest patch of nothing and you find galaxies. You assume that what you're seeing is reality, that the lights are the things that matter and the dark is just the space between. But you're looking at a stage set. The stars, the galaxies, the glowing nebulae, all of it is window dressing. The real universe, the one that actually controls how everything moves and behaves, is invisible. You're surrounded by it right now. Dark matter is passing through your body as you read this. Dark energy is stretching the space between your atoms, pushing the walls of your room outward by distances too small to measure. And you feel nothing. You see nothing. The entire structure of reality is built on components you have no direct access to. We spent thousands of years staring at the visible 5% and assuming it was everything. Then we spent another century discovering that we were wrong. And now we're standing in a universe we barely recognize, trying to figure out what the other 95% actually is. Nobody knows. That's the uncomfortable truth. We have names for these things: dark matter, dark energy. Names that sound confident, like we know what we're talking about. But they're placeholders. Labels we stuck on gaps in our understanding, because calling something dark matter sounds better than admitting we have no idea what it is. Physicists have theories, of course. Dark matter could be made of particles that only interact through gravity and the weak nuclear force. WIMPs, they call them, weakly interacting massive particles. Or it could be axions, hypothetical particles so light and so weakly interacting that detecting one would be like catching a whisper in a hurricane. Or maybe it's primordial black holes, tiny dense remnants left over from the first moments after the Big Bang, drifting through space in numbers large enough to account for all the missing mass. Or maybe it's none of those things. Maybe it's something we haven't thought of yet. Something so far outside our current understanding of physics that we don't even have the vocabulary to describe it. Dark energy is even worse. At least with dark matter, we can see its effects clearly. Galaxies rotating too fast, light bending around invisible mass, gravitational lensing revealing structures we can't otherwise detect. Dark energy has effects too. The accelerating expansion, the stretching of space, but we have no mechanism for it. No particle, no field, no theory that fits comfortably into the standard model of physics. The leading explanation, if you can call it that, is that dark energy is the cosmological constant, a term Albert Einstein added to his equations of general relativity and then later called his biggest blunder. He introduced it to keep the universe static, because at the time everyone assumed the cosmos was unchanging. When Edwin Hubble discovered that the universe was expanding, Einstein removed the term, embarrassed that he'd fudged his own equations. Turns out he was right the first time, or half right. The cosmological constant, the idea that empty space has its own intrinsic energy, might be exactly what dark energy is. Space itself pushing outward, not because anything is moving through it, but because that's what space does. It expands, and the more of it there is, the faster the expansion gets. If that's true, and nobody is sure it is, then the universe is accelerating itself to death. Every second, space is getting bigger. Every second, galaxies are moving farther apart. And because dark energy fills all of space uniformly, the more space there is, the more dark energy there is, and the faster everything flies apart. Eventually, billions of years from now, galaxies outside our local cluster will recede so far and so fast that their light will never reach us. The universe will go dark, not because the stars burned out, but because the space between us and them grew faster than light could cross it. We'll be left in an island of a few dozen galaxies, surrounded by an expanding void, unable to see anything beyond our immediate neighborhood. The cosmic horizon will shrink. The universe will become a much smaller, much lonelier place. That's the fate waiting at the end of the line. Isolation, darkness, a cosmos where the only light left comes from the slow-dying embers of stars that ran out of fuel billions of years ago. But we're not there yet. Right now, the universe is still full enough that we can look outward and see other galaxies, other clusters, other structures scattered across billions of light years. We can still map the cosmic web, the vast network of filaments and voids that gives the universe its large-scale structure. We can still measure, still observe, still try to figure out what the hell we're actually looking at. And what we're looking at, when we take the full inventory, when we add up all the visible matter and all the dark matter and all the dark energy, and calculate the ratio of substance to volume, is a universe that is almost entirely empty. A cosmos where matter of any kind, visible or invisible, is the rare exception, where the default state of existence is void. 99.9999999999999999998% empty. That number isn't just a statistic, it's a statement about the nature of reality. The universe is not a place filled with things separated by small gaps. It's a void punctuated by occasional specks of matter. We live on one of those specks. We are made of those specks. And we spend our lives thinking the specks are what matters, but the void is winning. It always was. The emptiness isn't background, it's the main event. And the more we look, the more we realize that everything we thought we understood about the cosmos, every intuitive sense we have about what the universe is and how it works, is built on a foundation of profound misunderstanding. We thought the sky was full. It's not. We thought matter was the substance of reality. It's not. We thought we were looking at the whole picture. We weren't. We were looking at 5%, and the other 95% was hiding in plain sight, invisible, waiting for us to notice that the darkness between the stars isn't empty at all. It's filled with something else. Something we can't see, can't touch, can't detect except by watching how it pulls and pushes on the tiny fraction of the universe we do understand. And that invisible ocean, that vast sea of nothing and something all mixed together, is where the real story begins. The universe we've established is mostly empty. That's the headline. The shock, the number that rewrites your assumptions about what reality actually is. But empty is an abstract word. It's a concept, a statistic. To understand what that emptiness actually means, you need to zoom in. Not to galaxies, not to stars, to the spaces in between, to the places where even galaxies fear to tread. Welcome to the cosmic voids. The largest structures in the universe. The deepest, darkest, most desolate expanses of nothing that existence has ever produced. Regions so vast, so profoundly empty, that calling them voids barely does them justice. These aren't pockets of space, they aren't gaps, they're oceans. Entire seas of absence stretching across hundreds of millions of light years, containing almost nothing. No stars, no planets. No glowing nebulae, no swirling galaxies lighting up the dark, just void, pure, cold, uninterrupted void, and they make up roughly 80% of the universe's total volume. Let that sit for a second. 80%. Not the galaxies, not the bright shining galaxy clusters we photograph and catalogue and name. Those occupy maybe 20% of space, and that's being generous. The rest, the overwhelming majority, is void. The universe isn't a collection of galaxies separated by empty space. It's a collection of voids, with galaxies clinging to the edges like foam on an ocean wave. The largest of these voids, the Bootis void, spans roughly 250 million light-years across. For context, our entire Milky Way galaxy is about 100,000 light-years wide. You could line up 2,500 Milky Ways end-to-end and still not cross the Bootis void. It's a sphere of nothingness so large that light, traveling at 186,000 miles per second, takes 250 million years to cross from one side to the other. If you were standing at the edge of the Bootis void and you pointed a telescope into its center, you'd see almost nothing. A handful of galaxies scattered across an incomprehensible distance. 60 galaxies, give or take, in a volume that by all rights should contain thousands. 60 galaxies in 250 million light-years. That's not empty by accident, that's empty on purpose. That's the universe actively avoiding putting things there. For most of human history, we had no idea these voids existed. We couldn't. Telescopes in the 1800s and early 1900s could see distant galaxies, sure, but mapping the three-dimensional structure of the cosmos required more than pretty pictures. You needed distances. You needed to know not just where a galaxy was on the sky, but how far away it sat. And that meant measuring redshifts, the stretching of light caused by the expansion of the universe. The farther away a galaxy is, the more its light gets stretched toward the red end of the spectrum. For decades, astronomers collected redshifts one galaxy at a time. Slow work, tedious. By the late 1970s, they had maybe a few thousand galaxies mapped in 3 dimensions, enough to see some patterns, some clustering, but not enough to reveal the full architecture. Then in the 1980s, a team led by astronomers at the Harvard-Smithsonian Center for Astrophysics started a project called the CFA Redshift Survey. The goal was simple: map as many galaxies as possible, measure their distances, and build a 3-dimensional picture of the nearby universe. Not just a photograph, a map, a chart showing where things actually were in space. What they found was not what anyone expected. Galaxies weren't scattered randomly. They weren't sprinkled evenly across space like stars in a planetarium. They were organized, clumped. Galaxies gathered into clusters, and those clusters linked together into long filaments, great walls of galaxies stretching across hundreds of millions of light-years. And between those filaments, between those walls, there was nothing. Vast, empty bubbles with almost no galaxies inside. Voids. In 1984, Robert Kirshner, a young astronomer working at the University of Michigan, along with colleagues Augustus Oemler, Paul Schechter, and Stephen Schechtman, published a paper describing one of the first well-mapped voids. They'd been surveying galaxies in a region near the constellation Bootes, and they noticed a strange absence. A hole in the distribution, a place where galaxies should be, statistically speaking, but weren't. They called it the Bootes void. At first, they thought it might be a measurement error. Maybe they'd missed some galaxies, maybe the data was bad. So they looked again, deeper surveys, better instruments. The void didn't go away, it got bigger. More detailed maps revealed that the Bootes void wasn't an isolated feature. It was part of a larger pattern, a cosmic web of structure where galaxies lived on the surfaces of giant bubbles, and the insides of those bubbles were almost completely empty. Since then, astronomers have mapped hundreds of voids. Some are small, only a few tens of millions of light-years across. Others are enormous, rivaling the Bootes void in scale. The local void, a smaller structure sitting relatively close to our own galaxy, spans about 150 million light-years. We're not inside it, but we're near the edge, close enough that our motion through space is partly determined by the gravitational pull of the matter surrounding the void, tugging us away from the emptiness like a marble rolling off the side of a bowl. These voids aren't randomly scattered, they fit together. Imagine a pile of soap bubbles in a sink. Each bubble is a void, a hollow sphere of empty space. The soap film where the bubbles touch, that's where the galaxies are, that's the cosmic web. Long, thin filaments of galaxies wrapping around enormous empty regions, forming a structure that looks less like a random cloud and more like a sponge, or a foam, or, if you want to get poetic about it, the neural network of some vast, incomprehensible brain. The voids themselves, the insides of the bubbles, are where things get strange because they're not quite empty. They can't be. Space itself has properties, it has energy, it expands, And inside a void, where there's almost no matter to slow things down, that expansion runs wild. Dark energy, the mysterious force accelerating the universe's growth, dominates completely. Matter has gravity. Gravity pulls inward. Dark energy pushes outward. In a region full of galaxies, gravity wins locally, holding clusters together even as the universe expands around them. But in a void, there's almost no matter, almost no gravity. Dark energy is free to do whatever it wants. So voids expand faster than the rest of the universe. Not by a lot, but measurably. Space inside a void stretches more aggressively than space outside. Over billions of years, that difference compounds. The void gets emptier. Any matter that was there to begin with gets pushed toward the edges, toward the walls of the bubble where gravity from surrounding galaxy clusters can grab it. The void becomes a self-reinforcing absence. The emptier it gets, the faster it expands. The faster it expands, the emptier it gets. This isn't speculation. Astronomers have measured it. Surveys tracking the motion of galaxies near the edges of voids show that they're being pushed outward, accelerated by the expansion of space inside the void. It's subtle. You're not going to see a galaxy suddenly rocket away. But over millions of years, the effect is clear. Voids grow. They consume the space around them. They are, in a very real sense, the dominant structures in the universe, not because they contain the most matter, because they contain the least. Here's the math, and it's brutal. The average density of the universe, when you smooth everything out over the largest possible scales, is roughly 1 hydrogen atom per 10 cubic meters of space. That's already absurdly empty. A cube the size of a small bedroom containing 1 single atom. But that's the average. In a galaxy cluster where matter is densest, you might get a few hundred atoms per cubic meter. Still empty by human standards, but dense by cosmic ones. In a void, the density drops to 1 atom per 100 cubic meters, or 1 per 1,000. Some voids, the deepest, darkest ones, have densities closer to 1 atom per 10,000 cubic meters, a volume the size of an Olympic swimming pool containing a single hydrogen atom. That's it. 1 atom floating alone in 2.5 million liters of empty space. And it's not just visible matter that's missing. Dark matter, the invisible scaffolding that holds galaxies together, is also depleted in voids, not gone, but reduced. Surveys measuring the gravitational lensing effect around voids show that they contain roughly 50% less dark matter than the cosmic average, which makes sense. Dark matter follows the same rules as visible matter when it comes to gravity. It clumps, it clusters, it gathers into halos around galaxies and galaxy clusters. In a void, where there are almost no galaxies, there's almost no dark matter either. So what you're left with is the purest expression of space itself. A region where the only thing that matters, literally the only thing present in any significant quantity, is dark energy. The field, the force, the property of the vacuum that pushes everything apart. In a void, dark energy is king. It doesn't have to compete with gravity. It doesn't have to fight matter for control. It just expands, forever, accelerating. This raises an obvious question. Where did the voids come from? Why are they there? If the universe started as a hot, dense soup of matter and energy, all more or less evenly distributed, how did it end up with such lopsided structure? Why are galaxies arranged in filaments and walls? Why are voids so empty? The answer goes back to the beginning. Not the very beginning, not the Big Bang itself, but close. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that moment, space was filled with a plasma of electrons and protons, too hot for anything stable to exist. When things finally cooled, atoms clicked together, the plasma cleared, and light could travel freely for the first time. That light, stretched and cooled over nearly 14 billion years, is what we now detect as the cosmic microwave background, the faint afterglow of the Big Bang still shining faintly across the entire sky. Embedded in that afterglow are tiny temperature fluctuations, hot spots and cold spots, each one differing from the average by only a few millionths of a degree. Those fluctuations weren't random noise. They were the seeds of all the structure we see today. Regions that were slightly denser than average had slightly more gravity. They pulled in more matter. As they grew, they pulled in even more positive feedback. Runaway growth. Over hundreds of millions of years, those dense patches became the first stars, the first galaxies, the first clusters. But here's the thing. If some regions were denser than average, other regions had to be less dense than average. That's how averages work. And those underdense regions, the places where matter was just slightly more spread out, evolved in the opposite direction. They had less gravity, so matter flowed out of them toward the denser regions nearby. Over time, the underdense areas became voids. The dense areas became filaments and clusters. The structure grew, the web formed, the voids emptied. This process is called gravitational instability, and it's been running non-stop for nearly 14 billion years. Computer simulations modeling the evolution of the universe from the cosmic microwave background to the present day reproduce the structure we observe with stunning accuracy. You start with a nearly uniform distribution of matter, add tiny fluctuations, let gravity and dark energy do their thing, and out pops the cosmic web. Filaments, walls, voids, all of it emerging naturally from the physics. The voids aren't mistakes, they aren't defects, they're a necessary consequence of how structure forms in an expanding universe. You can't have dense regions without underdense regions. You can't have galaxy clusters without voids. They come as a package, the bright and the dark, the full and the empty. One doesn't exist without the other, but the voids aren't static. They're not finished. Even now, as you read this, they're still growing, still expanding, still pushing galaxies toward their edges. In a few billion years, the voids will be larger, emptier. The cosmic web will stretch thinner. The filaments connecting galaxy clusters will grow longer, more fragile. Eventually, the expansion will win. The web will snap. Clusters will drift apart, isolated in their own pockets of space, surrounded by voids so vast that light from one cluster will never reach another. That's the future, the end game, a universe where the voids have consumed everything, where the only light comes from dying stars in isolated islands of matter, separated by oceans of darkness so wide that even the fastest signal, even light itself, can't cross them. We're not there yet, but we're heading there, and the voids, patient and relentless, are leading the way. Standing at the edge of a void, if you could somehow float there in a spacecraft with a window, what would you see? Not much. The nearest galaxy might be tens of millions of light years away, a faint smudge barely visible against the black. Behind you, the galaxy cluster you came from would shine brightly, a dense knot of light, thousands of galaxies packed into a relatively small volume. But in front of you, in the direction of the void, there would be nothing, no stars, no nebulae, no glow, just black. Pure, unbroken black stretching as far as your instruments could measure. You'd feel the same way you feel now, normal, comfortable. Space inside a void isn't dangerous. It doesn't pull at you. It doesn't radiate. It's just empty. But the psychological weight of that emptiness would be crushing, knowing that the nearest object, the nearest anything, is farther away than the entire width of a galaxy. Knowing that if you pointed your spacecraft in any direction and flew at the speed of light, you wouldn't reach another galaxy for tens of millions of years. Knowing that you are alone in the most literal, most absolute sense of the word. That's what a void is. Not a place you can visit because the distances are too vast and the lifetimes too short, but a place you can imagine. A place that exists right now, occupying the majority of the universe's volume. A place where the default state of reality is not stars and planets and glowing clouds of gas. It's nothing, silence, darkness, the kind of emptiness that makes the void between Earth and the nearest star look crowded by comparison. And here's the thing that keeps cosmologists awake at night. We're learning that voids might not be completely empty. Recent observations, some of the most detailed surveys ever conducted, have found hints of something strange happening inside them. Faint signals, tiny fluctuations in the cosmic microwave background, gravitational effects that don't quite match what you'd expect from pure vacuum. Some researchers, the bold ones, the ones willing to stick their necks out, have started suggesting that voids might contain a kind of matter we've never detected before. Not dark matter, something else, a hypothetical substance some call dark fluid, a field that fills the voids, interacts weakly with light and matter, and contributes to the expansion without clumping the way dark matter does. The idea is speculative, controversial. Most physicists treat it with skepticism, and rightly so. Extraordinary claims require extraordinary evidence, and the evidence for dark fluid is circumstantial at best. But the fact that serious scientists are even discussing it tells you something important. The voids are not understood, not fully. We know they exist, we know they're empty, we know they expand, but we don't know if they're truly empty in the philosophical sense. We don't know if there's something lurking in that darkness, something so diffuse and so weakly interacting that we haven't figured out how to detect it yet. Maybe the voids are exactly what they seem, nothing, vacuum, space with no substance. Or maybe, and this is the unsettling possibility, maybe they're filled with something we can't see. Something that doesn't light up, something that doesn't pull or push in ways our instruments recognize, something that just sits there silent and invisible, occupying the largest structures in the universe while we fumble around in the bright, noisy 20%, trying to figure out what's real. Either way, the voids are winning. They've always been winning. The universe is not a place where matter dominates. It's a place where emptiness dominates, where the norm is void and the exception is stars. We live in the exception. We evolved in the exception. We spend our lives studying the exception, photographing it, cataloging it, celebrating it, and all the while, the voids sit quietly in the background, occupying 80% of existence, saying nothing, doing nothing, just being empty. The cosmic web, that beautiful interconnected structure of filaments and clusters, is impressive, stunning even. But it's not the main event, it's the outline, the framework. The thin shell of matter wrapped around enormous bubbles of nothing. The voids are the substance. The voids are the structure. The voids are what the universe actually is. And if you want to understand the cosmos, if you want to know what reality looks like at the largest scales, you can't just study the bright parts. You have to study the dark parts too, the empty parts, the parts where nothing happens, where nothing exists, where the only force at work is the slow, patient expansion of space itself, because that's where the future is written, in the voids, in the emptiness, in the growing oceans of nothing that will one day swallow everything we can see, leaving behind a universe so vast and so empty that even the memory of galaxies will fade into the dark. But the voids don't act alone. They're shaped by something, held in place by something. The walls of the bubbles, the filaments connecting the galaxy clusters, Those exist because gravity is pulling matter together, forming structures massive enough to resist the expansion. And that gravity, the force holding the cosmic web in place, comes from something we still don't fully understand, something invisible, something that outweighs every star, every planet, every atom of gas by a factor of 5 to 1. The scaffolding underneath, the hidden architecture, the mass that holds galaxies together and keeps the voids from consuming everything all at once. Dark matter. And that's where the story goes next. The voids are vast, but they don't drift alone. They're corralled, shaped, held in place by something pressing inward from the walls. The galaxy filaments wrapping around those enormous empty bubbles. Those aren't there by accident. They're anchored by gravity, pulled together by mass. Except when you add up all the stars, all the gas clouds, all the planets, all the atoms you can actually see with telescopes, the math doesn't work. There isn't enough visible mass to hold those structures together, not even close. Galaxies should be flying apart. Galaxy clusters should have disintegrated billions of years ago. The cosmic web should have collapsed or scattered depending on the forces involved. None of that happened. Something is holding everything together, something invisible, something that outweighs every star, every planet, every scrap of glowing matter by a factor of 5 or 6 to 1, something that doesn't emit light, doesn't absorb light, doesn't interact with photons in any way we can measure. It only does one thing: it pulls. Dark matter, the invisible scaffolding underneath reality, the skeleton of the universe. And the strangest part is that we only discovered it existed because things were moving wrong. The problem showed up in the 1930s, though nobody recognized it as a problem yet. Fritz Zwicky, a Swiss astronomer working at Caltech, was studying the Coma cluster, a massive grouping of more than 1,000 galaxies sitting roughly 300 million light-years away. He wanted to measure how massive the cluster was, so he did what any good physicist would do. He watched how the galaxies were moving. Galaxies in a cluster don't sit still. They orbit each other, held together by their mutual gravitational attraction. The faster they move, the more mass must be present to keep them from flying apart. It's the same principle that governs planets orbiting a star. Earth stays in orbit around the Sun because the Sun's gravity is strong enough to hold it. If the Sun suddenly lost 90% of its mass, Earth would drift off into space. The orbit would break. Zwicky measured the velocities of galaxies in the Coma cluster and ran the numbers. The galaxies were moving fast, too fast. If the only mass in the cluster came from the visible galaxies, those galaxies should have escaped millions of years ago. The cluster should have dissolved, but it hadn't. It was stable, old, long-lived. Zwicky calculated that the cluster needed roughly 400 times more mass than what he could see to explain the velocities he was measuring. 400 times. That wasn't a small discrepancy. That wasn't a rounding error. That was a universe-sized gap between observation and theory. He proposed a radical explanation. There must be invisible matter mixed in with the visible galaxies, matter that didn't shine, matter that didn't show up in photographs, matter that only revealed itself through gravity. He called it Dunkel Materie, dark matter. The name stuck, though the idea didn't, not at first. Most astronomers ignored Zwicky. He had a reputation for being difficult, abrasive, prone to wild speculation. His dark matter hypothesis was filed away as an interesting oddity and promptly forgotten. For 40 years the problem sat there, unresolved and mostly ignored. Then in the 1970s, an astronomer named Vera Rubin started looking at galaxies in a different way. She wasn't studying clusters. She was studying individual spiral galaxies, measuring how fast stars were orbiting at different distances from the galactic center. Spiral galaxies are shaped like disks. The center is bright, packed with stars. The outer edges are dimmer, more spread out. If you assume that most of the galaxy's mass is concentrated in the center, where the stars are brightest, then Newton's laws make a clear prediction. Stars close to the center should orbit quickly. Stars farther out should orbit more slowly, the same way planets farther from the Sun take longer to complete their orbits. Mercury zips around the Sun every 88 days. Neptune takes 165 years. The pattern should hold for galaxies too. It didn't. Rubin, working with astronomer Kent Ford at the Carnegie Institution of Washington, measured the rotation curves of dozens of spiral galaxies. They pointed their telescope at a galaxy, captured the light from stars at various distances from the center, and used the Doppler shift to calculate how fast those stars were moving. The data was unambiguous. Stars at the outer edges of galaxies were moving just as fast as stars near the center, in some cases faster. The rotation curve didn't drop off, it stayed flat. That should not happen. The only way to explain it was to assume that galaxies contained far more mass than anyone could see. Not just a little more, a lot more. And that extra mass had to be distributed in a way that visible matter wasn't. It had to form a halo, a vast spherical cloud of invisible materials surrounding the galaxy, extending far beyond the visible disk. Rubin published her results in the late 1970s and early 1980s. The evidence was overwhelming. Galaxy after galaxy showed the same pattern. Flat rotation curves, missing mass, an invisible halo. The astronomical community, which had ignored Zwicky's warnings for decades, could no longer pretend the problem didn't exist. The galaxies are not rotating as they should, Rubin said in interviews. Something is missing, and whatever it was, it outweighed the visible stars by a factor of at least 5 to 1. Dark matter wasn't speculation anymore. It was a requirement, a necessary component of the universe. Without it, galaxies made no sense. The laws of physics made no sense. Reality itself made no sense. So what is it? That's the question physicists have been trying to answer for 50 years, and the frustrating, humbling truth is that we still don't know. We have candidates, theories, possibilities, but no confirmed detection, no particle sitting in a lab that we can point to and say, there it is, that's dark matter. The leading candidate for decades has been something called a WIMP, weakly interacting massive particle. The name is awkward but descriptive. These hypothetical particles would be massive, meaning they'd have a lot more mass than everyday particles like electrons or protons. And they'd be weakly interacting, meaning they'd barely interact with normal matter at all. They wouldn't bounce off atoms. They wouldn't emit light. They'd pass through solid matter like ghosts, only occasionally interacting via the weak nuclear force or gravity. WIMPs are attractive because they solve multiple problems at once. Theories extending the standard model of particle physics, particularly supersymmetry, predict the existence of stable massive particles with exactly the properties you'd need for dark matter. And when you run the calculations, when you figure out how many of these particles would have been produced in the early universe and how many would have survived to the present day, you get a number that matches the observed dark matter density almost perfectly. Physicists call this the WIMP miracle. The mass and interaction strength predicted by theory just happens to produce the right amount of dark matter. It's too neat to be a coincidence, or at least that's what many physicists believed for a long time. The problem is, nobody has found one. Experiments designed to detect WIMPs have been running for decades. Deep underground labs, shielded from cosmic rays, filled with tanks of ultra-pure liquid xenon or other materials designed to register the faint recoil when a WIMP collides with an atomic nucleus. The detectors sit in silence, waiting for a signal. A tiny flash of light, a microscopic vibration. Anything that would confirm the particles are there. Nothing. Year after year, null results. The detectors get more sensitive, the experiments get bigger, and still nothing. Either WIMPs are rarer or more weakly interacting than the theories predicted, or they don't exist in the form we expected. That's forced physicists to look elsewhere. Enter the axion, another hypothetical particle originally proposed to solve a completely different problem in quantum chromodynamics. Axions would be extremely light, millions of times lighter than an electron, and they'd interact even more weakly than WIMPs. But there could be trillions of them passing through every square centimeter of space every second. Collectively, they could add up to the dark matter density we observe. Detecting axions is a different challenge. You're not looking for a single collision. You're looking for a faint signal produced when a massive number of axions convert into photons in the presence of a strong magnetic field. Experiments like ADMX, the Axion Dark Matter Experiment, have been running for years, slowly scanning through possible axion masses, searching for that signal. So far, nothing conclusive, but the search continues. There are other candidates too: sterile neutrinos, primordial black holes, exotic particles predicted by string theory. Each one has its advocates, its theoretical justification, its experimental search program, and each one so far has failed to produce a confirmed detection. This might sound like a crisis, like the whole dark matter idea is about to collapse under the weight of negative results. It isn't. Because while we haven't directly detected dark matter particles, the indirect evidence for dark matter's existence has only gotten stronger. We don't need to catch the particles to know they're there. We can see what they do. Gravitational lensing is one of the cleanest proofs. Einstein's general relativity predicts that mass bends space. Light traveling through bent space follows a curved path. So when light from a distant galaxy passes near a massive object, like a galaxy cluster, the light gets deflected. The distant galaxy appears distorted, stretched into arcs or rings. By measuring how much the light bends, you can calculate how much mass is doing the bending. In 2006, astronomers studying a pair of colliding galaxy clusters called the Bullet Cluster made a discovery that became one of the most famous pieces of evidence for dark matter. The Bullet Cluster is actually two clusters that smashed into each other at enormous speed. When the collision happened, the hot gas in each cluster, the visible matter, slammed together and slowed down. Gas is made of atoms, and atoms interact. They collide, they heat up, they radiate. The collision created a massive shockwave, glowing brightly in X-rays. But the dark matter didn't slow down. Dark matter doesn't collide. It doesn't interact with itself in any significant way. So while the gas piled up in the middle, the dark matter halos passed right through each other and kept going. Astronomers used gravitational lensing to map where the mass actually was. The lensing signal, the place where space was most severely bent, didn't line up with the glowing gas. It lined up with empty space on either side of the collision. Empty except for the dark matter halos that had passed through and kept moving. The separation was clean, unambiguous. The mass wasn't where the visible matter was. It was where the dark matter was supposed to be, according to theory. You could see the division with your own eyes in the images, glowing gas in the middle, mass measured by lensing, offset to the sides. Dark matter and visible matter separated in space, proving that they were distinct substances. Peter Medawar, a Nobel laureate, called it the greatest mystery in physics. John Ellis, a theoretical physicist, put it more directly. Dark matter binds galaxies together. Without it, they would fly apart. There's another line of evidence, maybe the strongest of all. The cosmic microwave background, that faint glow of radiation left over from the early universe, carries within it a detailed map of the conditions 380,000 years after the Big Bang. The tiny temperature fluctuations across the sky, hot spots and cold spots differing by only a few millionths of a degree, encode information about the density and composition of the universe at that time. When scientists analyze the pattern of those fluctuations, they find something remarkable. The data fits a specific model almost perfectly. It's called lambda CDM, lambda for dark energy, CDM for cold dark matter. The model predicts that the universe contains roughly 5% normal matter, 27% dark matter, and 68% dark energy. Those numbers aren't guesses. They're extracted from the data by fitting the observed pattern of fluctuations to the predictions of general relativity and particle physics. The fit is shockingly good. The Planck satellite, which mapped the cosmic microwave background from 2009 to 2013, produced measurements so precise that the uncertainty in the dark matter fraction is less than 1%. The universe contains dark matter. We know how much. We know how it behaves. We just don't know what it is, and that precision matters because it rules out alternatives. For decades, some physicists have argued that maybe we don't need dark matter at all. Maybe gravity just works differently on large scales. Modified Newtonian dynamics, or MUNDI, proposes that Newton's laws break down in regions of extremely weak gravitational acceleration, like the outer edges of galaxies. Tweak the equations, the argument goes, and you can explain the flat rotation curves without invoking invisible matter. IMOND works reasonably well for individual galaxies. It struggles with galaxy clusters, and it completely fails to reproduce the cosmic microwave background. The pattern of fluctuations we observe requires dark matter. You can't fit the data without it. MUND is elegant in some ways, but the universe doesn't care about elegance. It cares about what actually happened, and what actually happened involved a lot of dark matter. So the picture that's emerged over the last 50 years is this. Dark matter is real. It's not a placeholder. It's not a fudge factor. It's a component of the universe as fundamental as stars and planets, and there's a lot more of it than there is of us. It forms halos around galaxies, providing the gravitational glue that keeps them intact. It clumps into filaments and sheets on the largest scales, creating the cosmic web. Visible matter, the stuff we're made of, follows dark matter's lead. Stars and gas fall into dark matter halos and light up, revealing the structure underneath. Computer simulations of the universe's evolution from the Big Bang to the present day make this startlingly clear. Plug in the right amount of dark matter, let gravity do its work, and out comes the cosmic web. Long filaments, dense clusters, voids. The whole structure matches what we observe. Take the dark matter out, run the simulation again, and the structure collapses. Galaxies don't form, clusters don't hold together. The universe looks nothing like the universe we actually live in. The Millennium simulation, run in 2005, tracked the evolution of more than 10 billion dark matter particles from the early universe to the present. It produced a cosmic web that looked eerily like the real thing. The Illustracetum project, a more recent simulation that includes both dark matter and normal matter, goes even further. It shows how gas flows into dark matter halos, cools, forms stars, and builds galaxies. The visible universe in these simulations is essentially tracing out the invisible scaffolding laid down by dark matter billions of years ago. Dark matter is the skeleton, we're the skin, the decoration, the visible layer draped over a structure we can't see, and that structure isn't static, it's dynamic. Dark matter halos grow over time as smaller halos merge together. Galaxies collide and combine, driven by the gravity of their dark matter halos pulling them together. The filaments connecting galaxy clusters act like highways, channeling matter from voids toward dense regions. The voids expand, the filaments grow, the web stretches. Dark matter orchestrates all of it. Right now, as you sit reading this, dark matter is passing through you. Billions of particles, assuming they exist, streaming through your body every second. They don't interact. They don't collide. They don't deposit energy. They just pass through, as if you weren't there, and you don't notice. You can't notice. The universe's most abundant form of matter is completely invisible to everything you've ever used to sense the world. Your eyes detect light. Dark matter doesn't emit light. Your hands feel pressure when atoms push against other atoms. Dark matter doesn't push. It doesn't touch. Instruments built to detect particles rely on those particles interacting with the detector material. Dark matter barely interacts. It's designed by the laws of physics to be undetectable by almost every method we've ever invented. That's what makes the search so hard. We're trying to find something that refuses to announce itself, something that hides not because it wants to, but because that's what it is. Invisible, intangible, present only in its effects. The experiments keep running, deep underground, shielded from cosmic rays. Scientists operate detectors cooled to near absolute zero, waiting for a signal. A single WIMP collision, a faint axion conversion, anything. The Large Hadron Collider smashes protons together at energies high enough to, in theory, produce dark matter particles if they exist in the mass range the theories predict. So far, nothing, but the absence of evidence isn't evidence of absence. It just means we haven't looked hard enough, or in the right place, or with the right tools. And there are hints, tantalizing, frustrating, ambiguous hints, gamma-ray signals from the center of the Milky Way that might be produced by dark matter particles annihilating each other, or they might be pulsars, nobody's sure. Anomalies in cosmic ray data that could be explained by dark matter or by more mundane astrophysical processes. Every potential signal is followed by years of analysis, debate, and usually disappointment. The universe is noisy. Dark matter, by definition, is quiet. Picking out the signal from the noise is like trying to hear a whisper in a hurricane. But the search continues because the stakes are enormous. Finding dark matter wouldn't just solve a puzzle, it would rewrite physics. The standard model of particle physics, the theory that describes all known particles and forces, is incomplete. It doesn't include dark matter. It doesn't include gravity, not in a quantum sense. Discovering what dark matter actually is would open the door to new physics, new forces, new particles, a whole new layer of reality sitting underneath the one we're familiar with. Dark matter is the universe's best-kept secret, the largest component of the cosmos, the invisible majority, the scaffolding holding galaxies together and shaping the structure of everything we see. And we don't know what it is, we know it's there. We know how it behaves, we can map it, measure it, simulate it, but we can't touch it, we can't catch it. We can't pin it down and say, this is what the universe is mostly made of. That gap between what we know and what we don't, that's where the frontier is. The boundary between observation and theory, between the visible and the invisible, between the 5% we understand and the 27% that holds everything together while refusing to show its face. Dark matter is patient. It's been there since the beginning, shaping galaxies, building structure, pulling matter into place. And it will be there long after the last stars burn out. a silent, invisible web, holding the remnants of the universe together, pulling on nothing, anchoring everything, unseen and unknowable. But dark matter isn't the only invisible force at work. It pulls inward, gathering matter into galaxies and clusters, resisting the expansion of space. But there's another force doing the opposite, pushing outward, accelerating the expansion, driving galaxies apart faster and faster with each passing billion years. And that force, even stranger than dark matter, even less understood, makes up an even larger fraction of the universe, nearly 70%, the dominant component, the ultimate winner in the cosmic tug-of-war, dark energy, and it's where the story gets truly unsettling. We've established that dark matter exists. The evidence is overwhelming. Galaxy rotation curves stay flat when they should drop off. Galaxy clusters hold together with 10 times more mass than anyone can see. The cosmic microwave background won't fit the data unless you add 27% invisible matter to the recipe. Dark matter is real, it's necessary, it's the scaffolding underneath everything. But knowing something exists and understanding what it is are two entirely different problems. And right now, 50 years after Vera Rubin proved galaxies were rotating wrong, we're still stuck on the first part. We know dark matter is there. We can measure how much of it there is. We can map where it goes. We can watch it pull galaxies into place and hold clusters together against the expansion of space itself. What we can't do, what we still haven't managed after decades of trying, is catch it. No particle sitting in a detector, no signal that can't be explained away as background noise or instrumental error, no confirmed detection of the substance that makes up more than a quarter of the universe. And that failure, that decades-long string of null results, tells us something uncomfortable about the nature of reality. The universe is mostly made of things we can't see, and mostly held together by forces we barely understand. We're living on a thin, visible crust, floating on an invisible ocean, and we don't have a good map of what's underneath. Let's start with what we do understand, because the evidence for dark matter's existence is rock solid, even if the evidence for what it's made of remains frustratingly absent. The story begins in earnest in the 1970s with Vera Rubin, though the seeds were planted decades earlier by Fritz Zwicky, a man who had a habit of being right long before anyone else was willing to listen. Zwicky was studying the Coma cluster in the 1930s, watching how galaxies moved within that massive grouping of more than 1,000 galaxies bound together by gravity. He measured their velocities and calculated how much mass would be needed to keep them from flying apart. The number he got was absurd. The cluster needed 400 times more mass than what he could see in the visible galaxies. 400 times. That's not a missing planet or an overlooked star. That's a missing universe. He proposed that invisible matter, what he called dark matter, must be filling the cluster, holding it together, providing the gravitational glue that kept the galaxies from escaping. The astronomical community looked at his result, looked at his reputation for being difficult and contrarian, and filed his idea away under interesting but unproven. For 40 years, dark matter was Zwicky's problem, a peculiar anomaly in one galaxy cluster that probably had a simpler explanation if anyone bothered to look hard enough. Then Vera Rubin started looking at individual spiral galaxies. She wasn't interested in clusters. She wanted to understand how galaxies themselves were put together, how they rotated, how their stars orbited around the galactic center. She pointed a telescope at galaxy after galaxy, measured the Doppler shift of light coming from stars at various distances from the center, and plotted their velocities. The pattern should have been obvious. Stars near the center, where most of the visible mass was concentrated, should orbit quickly. Stars farther out, in the dimmer outer regions where the galaxy thinned out, should orbit more slowly. That's how planets behave around the Sun. Mercury races around in 88 days, Neptune takes 165 years. The farther you are from the gravitational center, the slower you move. Basic Newtonian physics. Rubin's data showed the opposite. Stars at the outer edges of galaxies were moving just as fast as stars near the center. Some were moving faster. The rotation curve, the graph plotting orbital speed against distance from the center, stayed flat. It didn't drop off. It didn't taper. It just kept going, flat as a Kansas highway, all the way out to the edge of the detectable disk and beyond. There was only one way to explain that. Galaxies had to contain far more mass than anyone could see, and that mass couldn't be concentrated in the center where the stars were. It had to be spread out in a vast spherical halo surrounding the galaxy, extending far beyond the visible disk. An invisible halo, massive, dark, providing enough gravity at large distances to keep the outer stars moving fast. Rubin measured dozens of galaxies. Every single one showed the same pattern: flat rotation curves, missing mass, dark matter halos. She published her results in the late 1970s and early 1980s, and this time the astronomical community couldn't ignore it. The evidence was too consistent, too widespread, too impossible to explain away. Dark matter wasn't Zwicky's eccentric hypothesis anymore. It was a requirement, a fundamental component of the universe. Galaxies didn't make sense without it. The laws of physics didn't make sense without it. Either dark matter was real, or gravity worked completely differently on large scales, and nobody was ready to throw out Newton and Einstein just yet. So what exactly was Rubin seeing? Why do galaxies rotate the way they do? Picture a spiral galaxy like a disk of stars, gas and dust, spinning around a dense central bulge. Most of the light comes from the center and the inner spiral arms where young bright stars are concentrated. The outer regions are dimmer, sparser, harder to see. If you only counted the light, you'd conclude that most of the galaxy's mass sits in the inner half. Now watch how the stars move. Close to the center, they orbit quickly, whipping around the galactic core in a few 100 million years. As you move outward, you'd expect the orbital speed to drop off, following Kepler's laws, the same laws that govern planetary orbits. But it doesn't. Stars in the outer disk keep orbiting at roughly the same speed as stars in the inner disk. Some even accelerate slightly. The only way that works is if there's a lot more mass farther out than the light suggests. That extra mass is dark matter. It forms a halo, a roughly spherical cloud of invisible particles surrounding the visible galaxy. The halo extends far beyond the stars, perhaps 2 or 3 times the radius of the visible disk, and it's massive. For a galaxy like the Milky Way, the dark matter halo outweighs all the visible stars, gas and dust, combined by a factor of about 10 to 1. 10 times more mass in the halo than in everything you can see. The visible galaxy is just the tip of the iceberg, the bright, shiny part floating on the surface. The bulk of the mass, the real structure holding the galaxy together, is invisible, submerged, hidden beneath the surface of what telescopes can detect. This isn't unique to our galaxy. Every spiral galaxy ever measured shows the same pattern: flat rotation curves, dark matter halos. The visible disk sitting at the center of a much larger invisible structure. And it's not just spirals. Elliptical galaxies, those football-shaped blobs of old stars with no spiral arms, also show evidence of dark matter. Measure the velocities of stars within an elliptical galaxy and the dispersion, the spread of speeds, is too high. The stars are moving too fast. The galaxy needs more mass than you can see to keep them gravitationally bound. Galaxy clusters show the same thing, only more dramatically. The Coma cluster, the same one Zwicky studied in the 1930s, has been measured with much better instruments since then. Modern observations confirm his result. The cluster contains roughly 10 times more mass than what's visible in stars and gas. The galaxies themselves are embedded in an enormous halo of dark matter, a cloud spanning millions of light-years, holding the whole cluster together. You can see this directly now, not just by measuring velocities, but by watching how light bends. That's gravitational lensing, one of the most powerful tools in modern astronomy, and it turned dark matter from an invisible hypothesis into something you can actually map. Einstein predicted gravitational lensing in 1915. General relativity says that mass bends space. Light traveling through bent space follows a curved path. So if light from a distant galaxy passes near a massive object like a galaxy cluster, the light gets deflected. The image of the distant galaxy appears distorted, stretched into arcs, or smeared into rings. The more massive the object in the foreground, the more the light bends. By measuring how much the light bends, you can calculate how much mass is doing the bending. And here's the key part. Gravitational lensing doesn't care whether the mass is visible or invisible. It doesn't care if the mass emits light or sits in total darkness. Mass bends space, light follows the curve. The lensing effect maps the total mass distribution, visible and dark combined. In the 1990s and 2000s, astronomers started using the Hubble Space Telescope to photograph distant galaxy clusters and look for lensing effects. What they found was stunning. Distant galaxies behind the clusters appeared stretched into long, thin arcs, distorted by the gravity of the cluster in the foreground. By analyzing the shapes and positions of those arcs, scientists could reconstruct the mass distribution of the cluster. They could build a map of where the matter was, regardless of whether it glowed. The maps showed exactly what Rubin and Zwicky had predicted. The mass wasn't concentrated where the visible galaxies were. It was spread out in a much larger halo, a smooth cloud of dark matter filling the space between and around the galaxies. The visible galaxies were just tracers, bright markers floating in a sea of invisible mass. One of the most famous examples is the galaxy cluster Abell 2218, sometimes called the cosmic horseshoe, because of the spectacular arc-shaped lensing feature it produces. A background galaxy sits almost perfectly aligned behind the cluster, and the cluster's gravity bends the light into a near-perfect ring. The mass distribution required to produce that ring doesn't match the distribution of visible galaxies. It matches the distribution of dark matter predicted by theory. The cluster is mostly dark matter. The galaxies are just the visible decoration. Gravitational lensing gave astronomers a direct way to map dark matter. You didn't have to infer its presence from velocities or rotation curves. You could see its effects directly in the distortion of background light, and the more clusters astronomers mapped, the clearer the picture became. Dark matter is everywhere. It outweighs visible matter by a huge margin, and it clumps into halos and filaments that define the large-scale structure of the universe. But the single most compelling piece of evidence, the observation that shut down most remaining skepticism about dark matter's existence, came from a pair of colliding galaxy clusters known as the Bullet Cluster. The Bullet Cluster is actually two clusters that slammed into each other at millions of miles per hour. When the collision happened, the hot gas in each cluster, the ordinary matter, collided and slowed down. Gas is made of atoms. Atoms interact. They crash into each other, heat up, radiate energy. The collision created a massive shock wave, glowing brilliantly in X-rays. NASA's Chandra, the 10th Ray Observatory, captured stunning images of the event. The hot gas from both clusters piled up in the middle, a bright glowing cloud marking the site of the impact. But something else happened during the collision, something invisible. The dark matter halos surrounding each cluster passed right through each other and kept going. Dark matter doesn't interact with itself in any significant way. It doesn't collide. It doesn't slow down. It's effectively collisionless. So while the gas piled up in the center, the dark matter halos sailed past each other and emerged on opposite sides of the collision, separated by millions of light years. Astronomers used gravitational lensing to map where the mass actually was. They measured how light from background galaxies was being bent and calculated the mass distribution of the system. The lensing signal, the place where space was most severely warped, didn't line up with the glowing gas. It lined up with empty space on either side of the collision, empty except for the dark matter halos. The separation was clean, unambiguous. You could see it with your own eyes in the images. Glowing gas in the middle, bright and obvious in X-rays. Mass, measured by lensing, offset to the sides. Dark matter and ordinary matter, spatially separated. Two different substances behaving in two different ways. The gas collided, the dark matter didn't. They split apart during the crash, proving beyond any reasonable doubt that dark matter and ordinary matter are distinct. That dark matter exists as a separate component of the universe, and that it doesn't interact with light or ordinary matter except through gravity. The bullet cluster became the smoking gun. The definitive proof that dark matter wasn't just a mathematical trick or a misunderstanding of gravity. It was real, physical, present, just invisible. Stanford Woosley, an astrophysicist at the University of California, Santa Cruz, put it simply after the bullet cluster observations were published in 2006. This is the most compelling evidence yet that dark matter exists. The clusters have done us a favor by colliding and separating the dark matter from the ordinary matter so we can see the difference. That separation matters because it rules out most alternative explanations. For years, some physicists argued that maybe we didn't need dark matter, maybe gravity just worked differently on large scales. Modified Newtonian dynamics, MOND, proposed tweaking the laws of gravity to explain galaxy rotation curves without invoking invisible mass. MOND worked reasonably well for individual galaxies. It had trouble with clusters, and it completely failed to explain the bullet cluster. If you modified gravity to produce the observed velocities and rotation curves, the lensing signal should still line up with the visible matter. Gravity is generated by mass. If the only mass present is the gas, then the lensing should follow the gas, but it doesn't. The lensing follows the invisible halos. The only way to explain that is to have actual mass present where the halos are. Invisible mass, dark matter. The bullet cluster killed MOND as a viable alternative. Dark matter won. So dark matter is real. It's necessary. It's everywhere. It outweighs visible matter by 5 or 6 to 1. And we have no idea what it's made of. The leading candidate for decades has been the WIMP, weakly interacting massive particle. The name is clunky but descriptive. These hypothetical particles would have a lot of mass, somewhere between 10 and 1,000 times the mass of a proton, and they'd interact very weakly with ordinary matter. They wouldn't bounce off atoms. They wouldn't emit or absorb light. They'd pass through solid matter like ghosts, only occasionally interacting via the weak nuclear force, one of the 4 fundamental forces of physics. WIMPs are attractive because they solve multiple problems at once. Theories extending the standard model of particle physics, particularly supersymmetry, predict the existence of stable massive particles with exactly the properties you'd need for dark matter. Supersymmetry, or SUSY, proposes that every particle in the Standard Model has a heavier partner. The lightest of those partners would be stable, massive, and weakly interacting, a perfect dark matter candidate. When physicists ran the numbers, when they calculated how many of these particles would have been produced in the early universe and how many would survive to the present day, they got a density that matched the observed dark matter density almost exactly. The mass and interaction strength predicted by theory just happened to produce the right amount of dark matter. Physicists called this the WIMP miracle. It was too neat to be a coincidence. WIMPs had to be the answer. Except nobody has found one. Experiments designed to detect WIMPs have been running for decades. Deep underground labs, shielded from cosmic rays, filled with tanks of ultra-pure liquid xenon or germanium. The idea is simple. If WIMPs are passing through the Earth constantly, a tiny fraction of them should occasionally collide with an atomic nucleus in the detector. That collision would cause the nucleus to recoil, producing a faint flash of light or a tiny vibration. Detect that signal, and you've found dark matter. The detectors sit in silence, waiting. Year after year, null results. The experiments get bigger, more sensitive. The Easy-On collaboration, operating a detector deep under a mountain in Italy, has been searching for WIMPs since the early 2000s. Each iteration of the experiment is more sensitive than the last. Easy-On 1T, the most recent version, ran from 2020 to 2025. It detected nothing, no WIMP signal above the background noise. The LUX Zeppelin experiment, operating in a former gold mine in South Dakota, started taking data in 2023. It's even more sensitive than xenon. It's designed to detect WIMP interactions down to extraordinarily low energies, covering the full range of predicted WIMP masses. So far, nothing. The detector is working, the background is under control, the sensitivity is exactly where it needs to be. And dark matter, if it's made of WIMPs, is refusing to show up. This is the problem. Either WIMPs are rarer or more weakly interacting than the theories predicted, pushing them below the detection threshold of even the most sensitive experiments, or they don't exist in the form we expected. Maybe dark matter isn't made of WIMPs at all. Maybe it's something else. Enter the axion. Originally proposed in 1977 to solve a completely different problem in quantum chromodynamics, axions are incredibly light particles, millions of times lighter than an electron. They'd interact even more weakly than WIMPs. But if they exist, there could be trillions of them passing through every square centimeter of space every second. Collectively, they could add up to the observed dark matter density. Detecting axions requires a different approach. You're not looking for a single collision, you're looking for a faint signal produced when a large number of axions convert into photons in the presence of a strong magnetic field. The Axion Dark Matter Experiment, ADMX, has been running for years, slowly scanning through possible axion masses, searching for that conversion signal. In 2023, the experiment detected something, a faint signal at a specific frequency that matched the theoretical prediction for axions. The team was cautious. They ran more tests. The signal disappeared. Further analysis showed it was instrumental noise, not axions. Another false alarm. The search continues. ADMX is still running, still scanning. Other experiments are being built, but axions like WIMPs remain undetected. Hypothetical. Possible but not proven. There are other candidates. Sterile neutrinos, hypothetical cousins of the known neutrinos that don't interact via the weak force and could be heavy enough to account for dark matter. Primordial black holes, tiny dense objects formed in the first moments after the Big Bang, too small to be detected individually but collectively massive enough to explain the missing mass. exotic particles predicted by string theory. Each one has its advocates, its theoretical justification, its experimental search program, and each one so far has failed to produce a confirmed detection. This isn't just frustrating, it's philosophically unsettling. The universe is mostly made of something we can't see, can't touch, can't detect, except by watching how it pulls on the things we can see. And after 50 years of searching, we still don't know what it is. We've built detectors deep underground, launched satellites into space, smashed particles together at the highest energies ever achieved by human technology, and dark matter has remained silent. That silence tells us something. It tells us that whatever dark matter is, it's even more elusive than we thought. It interacts so rarely, so weakly, that our best instruments can't catch it. Or maybe it's not a particle at all. Maybe it's a field, a property of space itself, something that doesn't fit into the standard model's particle framework. Or maybe, and this is the possibility nobody wants to admit, maybe we're looking in the wrong place entirely. The Large Hadron Collider, the most powerful particle accelerator ever built, has been smashing protons together since 2008. One of its goals was to produce dark matter particles in the collisions. If WIMPs exist and have the masses predicted by supersymmetry, the LHC should be able to create them. The experiments at the LHC have found the Higgs boson. They've measured particles to incredible precision. They've ruled out huge swaths of parameter space for supersymmetric particles, but they haven't found dark matter. No new particles with the right properties have shown up. That doesn't mean dark matter doesn't exist. It means dark matter, whatever it is, doesn't fit the simplest versions of the theories we built to explain it. The WIMP miracle, that neat coincidence where theory predicted exactly the right amount of dark matter, is looking less miraculous and more like wishful thinking. The universe doesn't care about our theories. It doesn't care how elegant the math is or how well the predictions line up. It does what it does, and our job is to figure out what that is. So where does that leave us? We know dark matter is there. We can map it. We can measure how much there is. We can watch it hold galaxies together and shape the cosmic web. We can see it in rotation curves, in lensing maps, in the separation of mass and light in colliding clusters. The evidence is overwhelming. But the substance itself, the actual particles or fields or whatever makes up that missing mass, remains hidden. Invisible not just to light, but to every detection method we've invented. Dark matter is passing through you right now. Billions of particles, assuming they're particles, streaming through your body every second. They don't interact. They don't leave a trace. They just pass through, as if you weren't there. And you don't notice. You can't notice. The universe's most abundant form of matter is completely invisible to every sense you have, every tool you've built, every clever experiment you've designed to catch it. That's the state of the field. 50 years after Vera Rubin proved galaxies were rotating wrong, decades of null results, trillions of dollars spent on experiments, and still dark matter refuses to announce itself. It sits there, silent and invisible, holding the universe together while scientists scramble to figure out what it is. The search will continue. New detectors are being built, new theories are being tested, new experiments are being designed, each one more sensitive than the last. Eventually, someone will catch it, a signal that can't be explained away, a particle that fits the profile, a field that matches the behavior. Or maybe, just maybe, we'll discover that dark matter is something so far outside our current understanding of physics that we don't even have the vocabulary to describe it yet. But here's the thing. Dark matter, as mysterious and frustrating as it isn't the strangest invisible component of the universe. It's not even the largest. Dark matter pulls inward, gathering mass into galaxies and clusters, holding structure together against the expansion of space. But there's another force doing the opposite, pushing outward, accelerating the expansion, driving galaxies apart faster and faster as time goes on. And that force makes up nearly 70% of the universe, more than twice as much as dark matter, more than 10 times as much as all the visible matter combined. Dark energy. And it's where the story stops making sense entirely. Dark matter pulls. That's what we just established. It gathers matter into galaxies, holds clusters together, creates the scaffolding of the cosmic web. It's the invisible glue keeping structure intact against the expansion of space. Gravity, even invisible gravity, pulls inward. That's what gravity does. It attracts, it gathers, it resists separation. So when astronomers in the late 1990s set out to measure how fast the universe's expansion was slowing down, they had every reason to expect a straightforward answer. The universe was expanding, yes. Edwin Hubble proved that in 1929. Galaxies were moving away from each other, carried outward by the stretching of space itself. But gravity, the combined pull of all the matter in the universe, visible and dark, should be acting like a brake, slowing things down. The expansion should be decelerating, gradually losing steam over billions of years. Two independent teams of astronomers spent the better part of the 1990s measuring distant supernovae, using them as cosmic mile markers to chart the expansion history of the universe. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins, were in a friendly race to answer the same question. How much is the universe's expansion slowing down? How hard is gravity pulling on the brakes? They expected to measure a deceleration, a gentle tapering off of the expansion rate. The only real question was how much. Would the universe slow enough to eventually stop expanding and collapse back in on itself in a big crunch? Or would it keep expanding forever, just more and more slowly, coasting toward a cold, dark future where galaxies drifted so far apart they could no longer see each other? The data said neither. The universe wasn't slowing down. It was speeding up. Galaxies weren't just moving away from each other, they were accelerating, flying apart faster and faster as time went on. The expansion of space itself was accelerating, and nothing in the standard model of cosmology predicted that. Nothing. When the teams first saw the results, they thought they'd made a mistake. Perlmutter's group spent months checking and rechecking their data, looking for systematic errors, instrumental glitches, calibration problems. They found nothing wrong. Schmidt's team did the same result. The supernovae were farther away than they should be, dimmer than they should be, which meant the universe had expanded more than expected in the time since those stars exploded billions of years ago. The only way to explain that was if the expansion had accelerated. Both teams announced their findings in 1998, within months of each other. The universe is accelerating, not slowing down, accelerating. Something is pushing it, something with enough force to overpower the gravitational pull of every star, every galaxy, every clump of dark matter in the cosmos. Something that fills all of space, grows stronger as space expands, and has been quietly dominating the universe's behavior for the last few billion years. They called it dark energy. Not a great name, not a descriptive name, just another placeholder label stuck on another gap in our understanding. Dark because we can't see it. Energy because it behaves like a kind of pressure, a force field permeating space. But calling it dark energy doesn't tell you what it is any more than calling something dark matter tells you what that is. It's a name for our ignorance, a label we put on the problem while we scramble to figure out what's actually going on. The discovery sent shockwaves through the physics community, not because it was elegant or beautiful or satisfying, because it was completely unexpected. The universe wasn't supposed to do this. Expansion slowing down, fine. That made sense. Gravity pulls inward. Mass attracts mass. The expansion should slow, but acceleration, that required something new, something that wasn't in the equations, something that violated every intuitive sense physicists had about how the cosmos should behave, and the numbers were absurd. When astronomers calculated how much dark energy would be needed to produce the observed acceleration, they arrived at a figure that redefined the entire cosmic inventory. Dark energy doesn't just exist, it dominates. It accounts for roughly 68% of the total mass energy content of the universe. 68%, more than twice as much as dark matter. More than 10 times as much as all the visible matter combined. The single largest component of reality is something we discovered by accident 25 years ago and still don't understand. Let's back up and explain how anyone measures the expansion of the universe in the first place, because the method is both brilliant and absurdly difficult. You need two pieces of information for every distant object you observe: how far away it is and how fast it's moving. The speed part is easy. Light from distant galaxies gets stretched by the expansion of space, shifting toward the red end of the spectrum. Measure that redshift and you know how fast the galaxy is receding. The farther away something is, the faster it moves, which is exactly what you'd expect in an expanding universe. The distance part is harder. Much harder. When you look at a distant galaxy through a telescope, you see a tiny smudge of light. How far away is it? 1,000,000 light years? 1 billion? 10 billion? You can't tell just by looking. The galaxy could be faint because it's far away, or faint because it's just a dim galaxy sitting relatively close. You need a standard candle, an object with a known intrinsic brightness, something that always shines with the same luminosity no matter where it is in the universe. Measure how bright it looks from Earth, compare that to how bright it actually is, and the difference tells you the distance. The dimmer it looks, the farther away it must be. Basic inverse square law. For most of the 20th century, astronomers used a type of star called a Cepheid variable as their standard candle. Cepheids are massive stars that pulsate, brightening and dimming in a regular cycle. The period of the pulsation, how long it takes to go from bright to dim and back again, is directly related to the star's intrinsic luminosity. Measure the period and you know how bright the star actually is. Measure how bright it looks and you've got the distance. Cepheids work beautifully for nearby galaxies. Hubble used them to prove the universe was expanding in the first place. But they're not bright enough to see across billions of light years. If you want to measure the expansion history of the universe, if you want to look back billions of years and see how fast things were moving in the distant past, you need a brighter standard candle. You need something that can be seen halfway across the observable universe. Enter the Type 1a supernova. A Type 1a supernova is the explosion of a white dwarf star that has been siphoning mass from a companion star in a binary system. White dwarfs are the dense collapsed cores left behind when a sun-like star runs out of fuel. They're small, about the size of Earth, but incredibly massive, packing roughly the mass of the Sun into a sphere the size of a planet. When a white dwarf pulls enough matter off its companion, it crosses a threshold called the Chandrasekhar limit, about 1.4 times the mass of the Sun. At that point, the white dwarf can no longer support itself. It collapses. The collapse triggers a runaway thermonuclear explosion that tears the star apart in a blast so bright it can outshine an entire galaxy for weeks. Here's the key. Because all Type 1a supernovae explode at roughly the same mass, They all explode with roughly the same energy. They all reach roughly the same peak brightness. That makes them nearly perfect standard candles. Find a Type 1a supernova in a distant galaxy, measure how bright it looks, and you can calculate how far away the galaxy is with remarkable precision. By the mid-1990s, telescopes and digital cameras had improved to the point where astronomers could detect these supernovae billions of light-years away, distant enough to see the universe as it was billions of years ago, distant enough to measure how fast the universe was expanding in the past, and compare that to how fast it's expanding now. That's what the two teams set out to do. Find dozens of distant Type 1a supernovae, measure their distances and redshifts, and plot how the expansion rate had changed over cosmic history. They expected to see deceleration, a curve showing the expansion slowing down over time. What they got instead was the opposite. The supernovae were dimmer than expected. That meant they were farther away than expected. That meant the universe had expanded more than it should have in the time since those stars exploded. The expansion wasn't slowing down, it was speeding up. The implications were staggering. If the expansion was accelerating, something had to be driving it. Gravity couldn't do it. Gravity pulls inward. It slows expansion. It doesn't speed it up. Whatever was causing the acceleration had to be something else. A force that pushed outward, a kind of anti-gravity, and it had to be strong, powerful enough to overpower the combined gravitational pull of all the matter in the universe. The obvious candidate, the first place physicists looked, was something Albert Einstein had proposed and then discarded more than 80 years earlier: the cosmological constant, lambda, a term Einstein added to his equations of general relativity in 1917 to keep the universe static. At the time, everyone assumed the universe was unchanging, eternal and stable, but Einstein's equations didn't naturally produce a static universe. Matter, with its gravity, wanted to pull everything together. Left to its own devices, the universe should collapse. Einstein didn't like that. He wanted a static cosmos. So he added a term to his equations, a kind of energy inherent in space itself, that pushed outward with just the right strength to balance gravity and keep the universe from collapsing. He called it the cosmological constant. 12 years later, Edwin Hubble discovered that the universe wasn't static at all. It was expanding. Galaxies were moving apart. The cosmos was dynamic, not frozen. Einstein, realizing his cosmological constant was unnecessary, removed the term and reportedly called it his biggest blunder. He'd had the chance to predict the expansion of the universe from pure theory and missed it because he was too attached to the idea of a static cosmos. For decades after that, the cosmological constant was dead, discarded, a mistake. Nobody thought about it. Nobody needed it. The universe was expanding. Gravity was slowing it down. And that was the whole story. Simple, clean, elegant. Then, in 1998, the supernova teams discovered the expansion was accelerating, and physicists went scrambling back to Einstein's equations. Maybe the cosmological constant wasn't a blunder. Maybe it was real. Maybe space itself has an intrinsic energy, a property of the vacuum that creates a kind of outward pressure, a negative pressure, technically, which sounds like a contradiction but makes sense in the context of general relativity. Negative pressure means tension, stretching. It means space wants to expand, and the more space there is, the more of this energy there is, and the harder it pushes. If that's true, if the cosmological constant is real, then Einstein was right the first time. He just had the magnitude wrong. The constant isn't strong enough to hold the universe static. It's too weak for that. But it's strong enough to accelerate the expansion once the universe has grown large enough and the density of matter has dropped low enough. For the first several billion years after the Big Bang, matter dominated. Gravity was in control, the expansion slowed, but as the universe expanded, matter got more and more spread out. Its density dropped, its gravitational pull weakened, and eventually, around 5 or 6 billion years ago, the cosmological constant took over. Dark energy started winning. The expansion began to accelerate. We are living in the era of acceleration. Dark energy is in charge now, and it's never letting go. The 1998 discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. The Nobel Committee called it one of the most important scientific discoveries of the century. Publications like Nature and Science hailed it as revolutionary, a complete redrawing of our understanding of the cosmos. And they weren't exaggerating. This wasn't a minor adjustment to the model. It was a fundamental rewrite. Before 1998, the universe's future looked grim but comprehensible. Either the expansion would slow enough to stop and reverse, leading to a big crunch where everything collapsed back into a singularity, or it would keep expanding forever, just more and more slowly, eventually leaving galaxies isolated and alone in an empty void. Both scenarios made sense. Both followed from the physics. After 1998, the future looked different, darker, more certain, and more desolate. If dark energy is real, if the cosmological constant is driving the acceleration, then the universe will expand forever, not just coast to a stop, accelerate forever. Galaxies will drift apart faster and faster. Eventually, distant galaxies will recede so quickly that their light will never reach us. The observable universe will shrink. Billions of years from now, an astronomer in the Milky Way, assuming anyone is still around to look, will see a sky almost completely empty. A few dozen nearby galaxies in our local cluster, gravitationally bound together, surrounded by an infinite dark void. No distant galaxies, no cosmic microwave background. No evidence that the universe was ever anything other than a small island of matter floating in eternal emptiness. That's the big freeze, the heat death of the universe. A cosmos that expands forever, growing colder and emptier with each passing eon, until even the stars burn out, and the only light comes from the faint glow of dying embers drifting through a space so vast and so empty that nothing will ever find anything else again. It's not a quick death. It's a slow fade into darkness that takes trillions of years, but it's inevitable. If dark energy is what we think it is, the universe's fate is sealed. The cosmological constant explains the observations, but it raises a deeper problem, one that makes physicists deeply uncomfortable. If dark energy is a property of the vacuum, if it's energy inherent in empty space itself, then you should be able to calculate how much energy the vacuum has using quantum field theory. Physicists have done that calculation. The number they get is wrong. Not slightly wrong. Catastrophically wrong. Off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's the worst prediction in the history of physics. By far. The vacuum should have an enormous amount of energy, according to quantum mechanics. Particles and antiparticles constantly pop in and out of existence in empty space, borrowing energy from the vacuum for brief moments before annihilating each other. That activity should contribute to the vacuum energy. When you add it all up, the result is huge. But the actual observed value of dark energy, the cosmological constant that's accelerating the universe, is tiny. 120 orders of magnitude smaller than the theory predicts. Nobody knows why. Nobody has a good explanation. It's one of the biggest unsolved problems in physics. Some physicists have speculated that the cosmological constant isn't actually constant. Maybe it's a dynamic field, something that changes over time. They call this idea quintessence, a term borrowed from ancient philosophy referring to a fifth element beyond Earth: water, air, and fire. Quintessence would be a field permeating space, similar to dark energy, but with the ability to evolve. The universe has an edge, not a physical edge, not a wall you can touch or a boundary you can cross, but an edge nonetheless, a horizon beyond which nothing, no matter how bright, no matter how close it actually is in space, can ever send its light to us, and that horizon is shrinking. Right now, as you sit reading this, galaxies are vanishing across that edge, not because they're dying, not because they're exploding or collapsing or fading away, because the space between us and them is growing so fast that their light, traveling at the maximum speed anything in the universe can travel, will never make it across the gap. Those galaxies are still there, they're still shining. They're just gone, forever. Erased from our view not by destruction, but by distance, by expansion, by the relentless, accelerating push of dark energy stretching space itself faster than light can cross it. Welcome to the vanishing horizon, the cosmic event horizon, the boundary of the observable universe. And it's not a fixed line, it's moving inward toward us, swallowing galaxies by the billions. Every year, more galaxies cross that line and disappear. Every year, the universe we can see gets a little bit smaller, a little bit emptier, a little bit more lonely. And there's nothing anyone can do to stop it. Let's start with what the observable universe actually is, because the term gets thrown around a lot and most people don't realize how strange the concept is. The observable universe is not the same thing as the universe. The universe, capital U, is everything. All of space, all of matter, all of the galaxies, all of the stars, all of the voids stretching in every direction as far as anything goes. It could be infinite. It could be finite. We don't know. What we do know is that we can't see all of it. We can only see a small bubble around us, defined not by how far space extends, but by how far light has been able to travel since the Big Bang. Light is fast. 186,000 miles per second, fast enough to circle the Earth more than 7 times in 1 second. But the universe is old, 13.8 billion years old. So the farthest light that could possibly reach us is light that's been traveling for 13.8 billion years. That puts a limit on what we can see. A sphere around us, roughly 46.5 billion light-years in radius. Everything inside that sphere, that's the observable universe. Everything outside it might as well not exist as far as we're concerned, because the light from those regions hasn't had time to reach us yet. Wait, you're thinking, if the universe is 13.8 billion years old, why is the observable universe 46.5 billion light-years across and not 13.8 billion? Good question. The answer is expansion. While light was traveling toward us, the space it was traveling through was expanding, stretching. The galaxies that emitted the light we're seeing now were much closer when the light left them. Over billions of years, space expanded, carrying those galaxies farther away, and the light had to cover more distance than it would have in a static universe. By the time the light reaches us, the galaxy it came from is much farther away than the number of years the light has been traveling. The math works out to 46.5 billion light-years. That's the radius of the observable universe, the edge of what we can theoretically see. But here's the thing, the edge isn't static. It's not a fixed boundary sitting out there waiting for us to map it. It's dynamic, moving. And because of dark energy, because of the accelerating expansion, the edge is not moving outward anymore. It's moving inward. The observable universe is shrinking. That sounds wrong. If light keeps traveling toward us, if we keep waiting, shouldn't we be able to see farther and farther? Shouldn't the observable universe keep growing as more light from distant regions finally arrives? That's what would happen in a universe that was expanding at a constant rate or slowing down. But we're not in that universe. We're in an accelerating universe, and acceleration changes everything. Here's how it works. Imagine a galaxy sitting at the edge of the observable universe, just barely inside the boundary. Light from that galaxy is traveling toward us right now, but the space between us and that galaxy is expanding, stretching, and because of dark energy, the expansion is accelerating. Every second, the amount of space between us grows a little bit faster. At some point, the expansion becomes so fast that even though light from the galaxy is moving toward us at the speed of light, it's not gaining ground. It's like running on a treadmill that keeps speeding up. You're running as fast as you can, but the treadmill is accelerating faster than you can run, so you end up moving backward relative to the room. That's what's happening to light from distant galaxies. The light is traveling toward us at the maximum speed allowed by physics, but the space it's traveling through is expanding faster than that. The light isn't getting closer, it's getting farther away, and eventually the galaxy crosses a threshold, the cosmic event horizon. The point where the expansion is so fast that light emitted now will never ever reach us, no matter how long we wait. The galaxy has crossed the boundary, it's gone, and it's not just one galaxy, it's billions of them. Right now, at this moment, galaxies are crossing that horizon, vanishing from the observable universe. Not because they've moved in any physical sense, they haven't gone anywhere. They're sitting exactly where they've always been. But the space between us and them has expanded so much, so fast, that the light they're emitting now will never bridge the gap. We can still see the light they emitted in the past, the light that's already on its way, but once that light arrives, there won't be any more. The galaxy will fade, dim, redshift into oblivion, and then it will disappear forever. This isn't a distant future problem. This isn't something that might happen in 1 trillion years. It's happening now. Astronomers estimate that galaxies beyond about 16 billion light-years are already receding faster than the speed of light. They've already crossed the event horizon. The light we're seeing from those galaxies right now is ancient light, emitted billions of years ago when they were closer and still inside the boundary. But the galaxies themselves, as they exist right now, are unreachable. We will never see what they look like today. We will never know what happened to them. They are, for all practical purposes, gone. And the boundary keeps moving inward, closer, swallowing more galaxies every year, every century, every millennium. The observable universe is shrinking, and there's no way to stop it. Dark energy is in charge, and dark energy doesn't negotiate. Let's talk about what this actually looks like, because the mechanics are as elegant as they are disturbing. Light from a distant galaxy gets stretched as it travels through expanding space. That's cosmological redshift. The wavelength of the light increases, shifting from blue toward red. The farther the galaxy, the more the light gets stretched, and the higher the redshift. Astronomers measure redshift as a number, usually labeled Z. A redshift of Z equals 1 means the light has been stretched by a factor of 2. The wavelength is twice as long as it was when the photons left the galaxy. A redshift of Z equals 10 means the wavelength has been stretched by a factor of 11. The light that left as ultraviolet arrives as infrared. Right now, the most distant galaxies we can see have redshifts around Z equals 13 or 14. We're seeing those galaxies as they existed less than 300 million years after the Big Bang. The light has been traveling toward us for more than 13 billion years. Over that time, space expanded so much that the wavelength stretched by a factor of 14. What left as ultraviolet light arrives as deep infrared, barely detectable even by the James Webb Space Telescope. But there's a limit to how far we can see, and it's not set by our telescopes, it's set by physics. The cosmic microwave background, that faint glow left over from when the universe was 380,000 years old, has a redshift of about Z equals 1000. The light from that era has been stretched by a factor of 1000. What was visible light back then is now microwave radiation. That's the oldest light we can detect, the farthest we can see. Beyond that, the universe was opaque. Hot plasma filled with free electrons that scattered light in every direction. No photons from before that era can reach us. The cosmic microwave background is the wall, the ultimate horizon. Except even that horizon is shrinking. Not because the cosmic microwave background is moving. It's not. It's everywhere, a shell of ancient light surrounding us on all sides. But the photons from the most distant parts of that shell are being stretched so much, so aggressively, that they're red shifting out of detectability. In a few billion years, maybe less, the cosmic microwave background will be stretched into radio waves with wavelengths longer than anything our instruments can detect. The signal will fade into the noise, and future astronomers, if there are any, will lose the single most important piece of evidence we have about the early universe. The afterglow of the Big Bang will vanish, not because it stopped existing, because it got stretched too far to see. The same thing is happening to galaxies. The farthest galaxies we can see right now are already redshifted to the point where only the most powerful infrared telescopes can detect them. In a billion years, those galaxies will be redshifted even further. Their light will stretch into wavelengths so long that no conceivable telescope will be able to pick them up. They'll vanish, and new galaxies, the ones sitting just inside the current boundary of the observable universe, will take their place at the edge for a while. Then they'll redshift out of view too. This is the conveyor belt of cosmic extinction. Galaxies being carried across the event horizon, one by one, swallowed by the expansion, and there's no getting them back. Once a galaxy crosses that line, it's gone. Forever. You can't send a signal to it. You can't receive a signal from it. You can't know what's happening there. It exists, somewhere out in the unreachable vastness of space, but it's as inaccessible as if it had been erased from existence entirely. And the boundary isn't some distant abstraction. It's close, closer than you'd think. Right now, the observable universe contains roughly 2 trillion galaxies. That's the best estimate we have. 2 trillion galaxies scattered across a sphere 46.5 billion light-years in radius. Sounds like a lot. It is a lot. But the vast majority of those galaxies, more than 99% of them, are already doomed. They're so far away that even though we can see them now, they're receding faster than the speed of light. They've crossed the horizon. They're gone. We're just seeing the last light they sent before disappearing. Only a tiny fraction of galaxies, the ones in our local neighborhood, are close enough that their light will keep reaching us indefinitely. And that fraction is small, very small. The Milky Way sits in a group of galaxies called the Local Group, a gravitationally bound cluster containing about 50 galaxies. The largest members are the Milky Way, Andromeda, and Triangulum. The rest are smaller dwarf galaxies orbiting the big ones. That's it, 50 galaxies, gravitationally bound together tightly enough that the expansion of space can't pull them apart. Beyond the Local Group, almost everything is receding. The Virgo cluster, a massive collection of more than 1,000 galaxies sitting about 50 million light-years away, is moving away from us, not because it's traveling through space, but because space itself is expanding between us and it. Eventually, the Virgo cluster will redshift out of view. The galaxies will fade, dim, disappear. Same with the Comma cluster. Same with every other galaxy cluster we can see. They're all crossing the horizon, all vanishing. In a few billion years, maybe 10 billion, the observable universe will contain only the local group, 50 galaxies. Everything else will be gone. The sky will be darker, emptier, lonelier, and astronomers living in that future, if there are any, will look out at the cosmos and see almost nothing. A handful of nearby galaxies, no distant clusters, no cosmic web, no visible structure on large scales, just a small island of matter floating in an infinite void, and they won't know. That's the disturbing part. They won't know the universe used to be full. They won't know there were ever trillions of galaxies scattered across billions of light years. They won't have the cosmic microwave background to study because it will have red shifted out of detectability. They won't have distant supernovae to measure because all the distant galaxies will have vanished. They'll look at their data, run their calculations, and conclude that the universe is small, static, eternal, a few dozen galaxies surrounded by infinite emptiness, and they'll be wrong, completely wrong. But they'll have no way to know it. We live in a special time, a brief window in cosmic history when the universe is still full enough to see, still young enough that the light from distant galaxies hasn't all red shifted away. We can look out and map the cosmic web. We can measure the expansion. We can detect the cosmic microwave background and decode the history of the universe from its faint glow. Future civilizations won't have that luxury. They'll be blind, isolated, ignorant of the true scale and history of the cosmos, and they'll never know what they're missing. This isn't speculation. This is the logical consequence of an accelerating universe. Astronomers have run the numbers. Simulations like the Millennium Run and the Eagle Project model the evolution of the cosmos over trillions of years, tracking how galaxies move and how the observable universe shrinks. The results are unambiguous. In 100 billion years, the observable universe will contain only the local group. In 1 trillion years, even some of the dwarf galaxies in the local group will have drifted too far to see. The observable universe will shrink to just a few galaxies, maybe just one. The Milky Way, or whatever it becomes after merging with Andromeda, sitting alone in an infinite dark ocean. And the isolation isn't just visual, it's informational. Science relies on observation. You can't study what you can't see. Future astronomers won't be able to confirm the Big Bang because they won't have the cosmic microwave background. They won't be able to measure the expansion rate because all the distant galaxies will be gone. They won't be able to map dark matter on large scales because there won't be large-scale structure left to map. Everything we know about cosmology, everything we've learned in the last 100 years, will be impossible to discover. The evidence will have vanished, erased by expansion. It's a humbling thought. We're lucky to live in an era when the universe is still observable. Lucky to have telescopes powerful enough to see distant galaxies before they disappear. Lucky to have the cosmic microwave background still faintly glowing in the microwave spectrum where we can detect it. A few billion years earlier, and the universe would have been too young, too hot, too chaotic to study. A few billion years later, and it will be too empty, too dark, too stretched out to make sense of. We're standing in a narrow window of time when the cosmos is both old enough to have structure and young enough that the structure is still visible. And that window is closing, fast, not on human timescales, obviously. The galaxies aren't going to disappear tomorrow or next year or even in the next million years. But on cosmic timescales, the ones that matter when you're talking about the life and death of the universe itself, The window is slamming shut. 10 billion years from now, most of the observable universe will be gone. 100 billion years from now, almost all of it. And there's nothing anyone can do to stop it. No technology, no matter how advanced, can reach across the event horizon. No signal, no spacecraft, no probe, nothing can cross that boundary. It's not a physical barrier, it's a consequence of geometry, of the way space itself is structured. Once a galaxy crosses the horizon, it's as unreachable as the interior of a black hole. Gone. Permanently. Erased from the observable universe. The term cosmologists use for this future is cosmic loneliness. It's not a scientific term. It's a poetic one, but it's accurate. Loneliness, isolation. A universe where the only galaxies you can see are the ones gravitationally bound to you, drifting together in a shrinking bubble of visibility while everything else fades into the dark. No neighbors, no distant lights. No evidence that the universe was ever anything other than a tiny cluster of galaxies surrounded by infinite emptiness. And here's the existential kicker. We're already alone. We just don't realize it yet. The galaxies we can see right now, the ones shining brightly in our telescopes, most of them are already unreachable. We're seeing them as they were billions of years ago. The light we're detecting left those galaxies when the universe was young, when they were closer, when the space between us was smaller. But those galaxies, as they exist right now in the present moment, are already gone. They've crossed the horizon. They're receding faster than light. We will never see what they look like today. We will never know what happened to them after the light we're seeing now left their stars. They are, in every meaningful sense, lost. The observable universe is a time machine, a record of the past. The farther you look, the farther back in time you see. The most distant galaxies we can detect existed when the universe was less than 300 million years old. We're seeing their infancy, their first stars, their first bursts of light. But those galaxies have had 13 billion years to evolve since then. They've grown, changed, maybe merged with other galaxies, maybe died. We'll never know. The light from their later years will never reach us. It's been stretched too far, red-shifted too much, or it's still traveling through space and won't arrive for billions of years, by which point the wavelength will be so long it's undetectable. We're ghosts looking at ghosts, observing a universe that no longer exists in the form we're seeing it. And the version that does exist, the present-day universe, is mostly hidden from us, invisible, receding faster than we can chase it. The Hubble Space Telescope, the James Webb Space Telescope, every other observatory we've built, they're all looking backward. They're mapping history, not the present. The present is inaccessible. The real universe, the one happening right now across billions of light years, is beyond our reach. We can only see where it's been, and even that record is fading. The evidence is being erased. The most distant galaxies are red, shifting out of view. The cosmic microwave background is dimming. The horizon is shrinking, and there's no way to recover what's being lost. Simulations from the Planck satellite, which mapped the cosmic microwave background in exquisite detail from 2009 to 2013, show how this plays out. The temperature fluctuations in the microwave background, those tiny hot and cold spots that encode the seeds of all cosmic structure, will stretch and fade as the background itself red shifts into radio waves. In 100 billion years, the signal will be so faint, so stretched, so buried in noise, that no instrument will be able to extract meaningful data from it. The cosmic microwave background will still exist. It will still surround us, but it will be invisible, a ghost of a signal, too faint to detect, too stretched to analyze, and with it will go the evidence for the Big Bang. the proof that the universe had a beginning. Future astronomers, looking at a sky containing only a handful of nearby galaxies, will have no reason to think the universe ever looked different. No expanding cosmos, no hot, dense origin, no primordial fireball. Just a static collection of galaxies sitting in a void that's always been there and always will be. They'll be wrong, but they'll have no data to prove it. That's the legacy of dark energy. Not just acceleration, isolation, ignorance, a universe that erases its own history, that hides its past so thoroughly that future observers will be unable to reconstruct it. And if it happened to them, if future civilizations will be blind to the history we can still see, then what are we blind to? What evidence has already vanished? What parts of cosmic history occurred so long ago or so far away that the light was stretched out of detectability before we ever evolved to look for it? We don't know. We can't know. The universe is accelerating, the horizon is shrinking, and the evidence is disappearing. We're standing on a shrinking island of observability, watching the ocean of darkness rise around us, swallowing everything we can see, leaving us more and more alone with each passing billion years. And there's no shore to swim to, no higher ground. Just the slow, relentless, unstoppable expansion of space itself, carrying the rest of the universe across a boundary we can never cross. This is the vanishing horizon. The cosmic event horizon, the edge of forever. And it's moving toward us, closer every second, swallowing galaxies by the billions, erasing the universe one light year at a time, and there's nothing we can do but watch and remember and try to understand as much as we can before the evidence fades and the darkness wins. But the story doesn't end with isolation. There's a deeper question beneath all of this. A question about origins and endings, about how the universe went from nothing to everything and how it will eventually return to something resembling nothing again. Because the voids, the dark matter, the dark energy, the vanishing horizon, all of it traces back to the beginning, to the first fraction of a second after the Big Bang, when quantum ripples in space-time seeded the structure that would grow into galaxies and clusters and voids. Those ripples are still echoing, still shaping the cosmos. And understanding where they came from and where they're going is the final piece of the puzzle, the echo of eternity. From quantum fluctuations to cosmic silence, that's where the story ends. Or begins, depending on how you look at it. We've spent this whole time building toward isolation, the voids expanding, dark energy accelerating, galaxies vanishing across the cosmic horizon, one by one, swallowed by the stretching of space. The observable universe shrinking into a tiny bubble containing only our local neighborhood, alone in an infinite dark ocean with no memory of what came before. That's where we left off. The end of visibility, the death of evidence, the universe erasing its own history, but the story doesn't start there. It starts in the opposite direction, not at the end, but at the beginning, not with silence and emptiness, but with noise and chaos. With the first fraction of a second after the Big Bang, when the universe was smaller than an atom, hotter than anything that exists today, and filled with quantum fluctuations so tiny, so random, that calling them structure feels like giving them too much credit. They were nothing, ripples in nothing. Vibrations in the fabric of space-time itself, so small that if you could somehow freeze the universe at that moment and zoom in with infinite magnification, you'd barely see them. Tiny bumps and dips in energy density scattered across a patch of space smaller than the period at the end of this sentence. Those ripples, those microscopic quantum hiccups in the earliest moments of existence, are the reason you're here. The reason galaxies exist. The reason stars formed. The reason there's structure in the universe at all, instead of a perfectly smooth, featureless soup of matter spread evenly across infinite space. Everything, and I mean everything, every galaxy cluster, every void, every filament in the cosmic web, every atom in your body traces back to quantum fluctuations that happened in the first 10 to the negative 36 seconds after the Big Bang. 10 to the negative 36 seconds. That's a decimal point, followed by 35 zeros and then a 1, a trillionth of a trillionth of a trillionth of a second. That's when it happened. That's when the seeds of all future structure were planted. And the mechanism that turned those seeds into galaxies has a name: inflation. Inflation is one of the strangest, most counterintuitive, and most important ideas in modern cosmology. The basic concept is simple. In the first tiny fraction of a second after the Big Bang, the universe didn't just expand, it inflated, exponentially, faster than anything has ever expanded before or since. Space itself doubled in size, then doubled again, over and over, more than 60 times in less time than it takes light to cross the width of a proton. The universe went from smaller than an atom to larger than a grapefruit in less than 10 to the negative 32 seconds. That's not fast expansion, that's insane expansion. Runaway expansion. Expansion driven by a field that cosmologists call the inflaton, a hypothetical form of energy that filled space and pushed outward with a force so strong that nothing, not even gravity, could slow it down. Nobody knows what the inflaton actually was. Nobody has detected it. It's not in the standard model of particle physics. It's a placeholder, a name for whatever caused inflation. But the effects of inflation are written all over the universe. You can see them in the cosmic microwave background. You can measure them in the distribution of galaxies. You can calculate them in the ratio of matter to energy. Inflation happened. The evidence is overwhelming. The question is why? The reason physicists invented inflation in the first place was to solve problems, big problems. Problems with the standard Big Bang model that didn't add up. One of those problems was called the flatness problem. When you measure the geometry of the universe, when you calculate how much it's curved by the total amount of mass and energy it contains, you get a number very close to zero. The universe is flat, not flat like a pancake. Flat in the sense that parallel lines stay parallel forever, that the angles of a triangle add up to exactly 180 degrees, that the large-scale geometry of space follows Euclidean rules. That might sound boring, but it's not. It's extremely strange. Because for the universe to be flat today, it had to be flat to an absurdly precise degree in the early universe. Off by even a tiny fraction, and the universe would have either collapsed back on itself within seconds, or expanded so fast that no structures could ever form. The fact that we're here, that galaxies exist, that the universe is still around after nearly 14 billion years, means the initial conditions had to be tuned to better than 1 part in 10 to the 60th. That's not a coincidence, that's a problem. Inflation solves it. If the universe inflated exponentially in that first fraction of a second, any curvature it started with got stretched flat. Think of it like blowing up a balloon. The surface of a balloon is curved, but if you blow it up big enough, any small patch of the surface starts to look flat. Inflate the universe by a factor of 10 to the 30 or more, and any curvature gets stretched out so much that the observable universe looks perfectly flat. Problem solved. Another problem was the horizon problem. The cosmic microwave background, that faint glow of radiation left over from when the universe was 380,000 years old, is remarkably uniform. The temperature is the same in every direction to within a few parts per 100,000. That's strange because regions of the microwave background on opposite sides of the sky are so far apart that, without inflation, light wouldn't have had time to travel between them. They should never have been in contact. They should have no reason to be the same temperature. It's like finding two isolated islands on opposite sides of the planet, with identical climates, identical ecosystems, and no way for them to have ever communicated. How did they end up the same? Inflation solves it. Before inflation, the entire observable universe was much smaller, small enough that different regions could be in contact, could exchange energy, could reach thermal equilibrium. Then inflation blew everything up so fast that regions that used to be next to each other got separated by billions of light years. But they remembered. They started at the same temperature, so they stayed at the same temperature even after inflation stretched them to opposite sides of the observable universe. Problem solved. But here's the really important part. Inflation didn't just solve problems. It made predictions. And one of those predictions was that quantum fluctuations, the random jitter inherent in the fabric of space-time at the smallest scales, would get stretched by inflation, amplified, turned into macroscopic variations in the density of matter and energy. Those variations, tiny differences in how much stuff was packed into different regions of space, would survive inflation and become the seeds of all future structure. Gravity would take those seeds and grow them. Dense regions would pull in more matter, becoming denser. Underdense regions would lose matter, becoming voids. Over billions of years, those tiny ripples would grow into galaxies, galaxy clusters, filaments, and the voids we've been talking about for the last 6 chapters. Inflation predicted that the cosmic microwave background should have tiny temperature fluctuations, hot spots and cold spots, variations of about 1 part in 100,000. And it predicted the pattern those fluctuations should follow, the sizes and shapes and distribution of the hot and cold spots, based on the quantum mechanics of the inflaton field. In 1992, NASA's COBE satellite, the Cosmic Background Explorer, detected those fluctuations for the first time. George Smoot, the lead scientist, called it seeing the face of God. Stephen Hawking called it the greatest discovery of the century. The fluctuations were there, exactly as predicted. Tiny variations in temperature, about plus or minus 200 microkelvin, scattered across the sky in a pattern that matched inflation's predictions almost perfectly. COBE couldn't measure the pattern in enough detail to be sure, so NASA built a better satellite. WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001 and spent 9 years mapping the cosmic microwave background with unprecedented precision. It measured the sizes of the hot and cold spots, the angles they subtended, the correlations between them, and extracted from that data a complete description of the early universe. How much normal matter it contained, how much dark matter, how much dark energy, how old it was, how fast it was expanding. And the shape of the fluctuations matched inflation's predictions to better than 1%. The universe had been inflated, the quantum ripples had been stretched, the seeds of structure had been planted. Then the European Space Agency built an even better satellite. Planck, launched in 2009, mapped the microwave background with sensitivity and resolution that pushed the limits of what's physically possible. It measured temperature variations down to a few millionths of a degree. It detected polarization patterns in the light, subtle twists in the orientation of the photons that encoded information about gravitational waves rippling through the early universe. And it confirmed everything WMAP had found, with even tighter error bars and even more detail. The cosmic microwave background is a snapshot of the universe 380,000 years after the Big Bang, and it shows exactly what inflation predicted: a nearly uniform glow with tiny ripples frozen in place, waiting for gravity to turn them into galaxies. Those ripples aren't just random noise. They're quantum fluctuations, actual, literal quantum fluctuations in the vacuum energy of the inflaton field, amplified to cosmological scales by the exponential expansion of space. Before inflation, those fluctuations existed only at the Planck scale, the smallest possible size allowed by physics, about 10 to the negative 35 meters. After inflation, they were stretched to scales of millions of light-years. Quantum mechanics, the physics of atoms and particles, and things too small to see, became the physics of galaxies and voids and structures, spanning a significant fraction of the observable universe. The boundary between the quantum world and the classical world got erased. The universe itself is a quantum object, and the proof is written across the sky in the pattern of the cosmic microwave background. Here's where it gets eerie. The ripples in the microwave background, those tiny hot and cold spots, are not uniform in size. They follow a specific statistical pattern. Some are large, spanning degrees across the sky. Some are small, spanning minutes of arc. When you plot the distribution, when you calculate how much variation exists at each angular scale, you get a curve, a power spectrum. And that curve has peaks and valleys, specific features that encode information about the physics of the early universe. The first peak, the tallest one, corresponds to the largest ripples, the ones that had the most time to grow before the microwave background was released. The height of that peak tells you how much normal matter the universe contains. The position of the peak tells you the geometry of space, whether it's flat or curved. The smaller peaks encode information about dark matter, dark energy, the speed of sound in the primordial plasma, even the existence of neutrinos. Planck measured that curve with absurd precision. The error bars on some of the peaks are less than 1%, and the curve matches the predictions of the simplest models of inflation almost exactly. The universe inflated. Quantum fluctuations got stretched. Gravity turned them into structure. The cosmic microwave background is the receipt, the proof, the smoking gun. But the story doesn't end there. The ripples in the microwave background are just the beginning. They're the blueprint. The map showing where matter would eventually gather and where it wouldn't. Over the next several 100 million years, those ripples grew. Dense regions got denser. Gravity pulled matter inward, forming clumps. Those clumps attracted more matter, positive feedback, runaway growth. The clumps became dark matter halos, vast clouds of invisible mass where the ripples had been slightly denser than average. Gas fell into those halos, heated up, cooled, and collapsed to form the first stars. The first stars formed galaxies. Galaxies formed clusters. Clusters linked together into filaments, and in between the filaments, where the ripples had been slightly underdense, matter flowed outward. The voids grew, emptied, expanded. The structure we see today, the cosmic web of filaments and voids, is the direct descendant of quantum fluctuations that happened 10 to the negative 36 seconds after the Big Bang. Think about that. The chair you're sitting on, the planet beneath your feet, the galaxy you live in, all of it traces back to a random quantum event in the first moment of existence. A ripple in space-time, amplified by inflation, grown by gravity over 13.8 billion years. If that ripple had been slightly different, if the quantum fluctuations had landed in a different pattern, the Milky Way wouldn't exist, the Sun wouldn't exist, you wouldn't exist. The structure of the universe is not deterministic, it's probabilistic, random. A cosmic roll of the dice played out at the Planck scale and stretched across billions of light years. Cosmologists call this the principle of cosmic variance. The pattern of fluctuations we observe in the cosmic microwave background is one realization of a random process. In another universe, another bubble of space that inflated separately, the pattern would be different. The locations of galaxies would be different. the shapes of voids would be different. There's no reason the universe had to look the way it does. It's an accident, a specific outcome of quantum randomness, frozen into structure by inflation and gravity. And here's the strangest part. We can see the quantum origin of that structure directly. The ripples in the cosmic microwave background follow a Gaussian distribution, a bell curve, the same statistical pattern that governs radioactive decay, coin flips, and every other random process in nature. Gaussian distributions come from adding up lots of independent random events, and quantum fluctuations in a vacuum are as random as anything in physics gets. The universe, at its largest scales, looks random because it is random. It's quantum mechanics writ large. The same equations that describe how electrons behave around an atom also describe how galaxies are distributed across the sky. Scale doesn't matter. Randomness is randomness. But randomness isn't chaos. Random doesn't mean unpredictable. You can't predict the outcome of a single coin flip, but you can predict the distribution of outcomes over 1 million coin flips. You can't predict where a specific galaxy will form, but you can predict the statistical properties of how galaxies cluster together. The cosmic microwave background gives us that prediction. It tells us exactly how much structure should exist at every scale, and observations of galaxies, clusters, and voids confirm it. The universe is random, but it's predictably random. The quantum ripples followed rules, and those rules produced the cosmos we see today. Now fast forward 13.8 billion years. The ripples have grown, the structure has matured, galaxies shine, stars burn, planets orbit. Life, somehow, emerged on at least one of those planets, maybe more. The universe looks full, active, alive. But it's not stable, it's not eternal. The same force that's accelerating the expansion, dark energy, the thing that's shrinking the observable universe and isolating galaxies, is also driving the universe toward its ultimate fate, the end state, the final configuration, the heat death. Heat death doesn't mean the universe gets hot. It means the opposite. It means the universe reaches maximum entropy, a state where no energy gradients exist, no work can be performed, no structures can form or survive. Everything evens out. Every hot spot cools. Every cold spot warms. Eventually, the temperature everywhere approaches absolute zero. Not quite zero, because quantum mechanics won't allow that, but close enough that it doesn't matter. The universe becomes a vast, dark, cold, empty expanse where nothing happens, ever, for all of eternity. The timeline for heat death is long, very long, longer than human brains are designed to process. Start with the stars. The universe is still making stars right now, pulling gas out of clouds and igniting it in nuclear fusion. But the gas is running out. The rate of star formation peaked a few billion years ago and has been declining ever since. In another few trillion years, the last stars will form. After that, no more. The existing stars will burn through their fuel and die. Small stars, red dwarfs, can burn for tens of trillions of years, but eventually they run out too. By about 10 trillion years from now, the last stars will fade. The universe will go dark. No more sunlight, no more starlight. Just the faint glow of cooling embers scattered across an expanding void. But there will still be objects, dead stars, white dwarfs, neutron stars, black holes, planets drifting in the dark, frozen solid, their surfaces colder than anything that exists today. For a while, those objects will remain, but gravity doesn't stop. Over unimaginably long timescales, quadrillions of years, gravitational interactions will slowly eject planets from their orbits. Galaxies, or what's left of them, will evaporate, flinging stars and dead remnants into the void. Some will fall into the central black hole. Most will drift away, alone, never to encounter another object again. The black holes will be the last holdouts, the largest ones. The supermassive black holes sitting at the centers of galaxies will survive for 10 to the 100 years. A 1 followed by 100 zeros. That's not just a long time, that's a time so long that calling it long doesn't mean anything. The current age of the universe is about 10 to the 10th years, 10 billion. 10 to the 100 is 10 to the 90th times longer than that. A span so vast that every star that has ever existed, every photon that has ever been emitted, every thought that has ever been thought, all of it happens in the first eye blink of that time. The universe's entire history so far is a rounding error compared to how long the black holes will sit there, slowly evaporating via Hawking radiation, leaking photons into the void one quantum at a time. Stephen Hawking figured out in the 1970s that black holes aren't perfectly black. Quantum effects near the event horizon allow particles to escape, carrying away energy. The black hole loses mass. Slowly, absurdly slowly. A solar mass black hole would take 10 to the 67 years to evaporate. A supermassive black hole weighing 1 billion times the mass of the Sun would take 10 to the 100 years, but eventually it happens. The black hole shrinks, gets smaller, lighter, and in the final moments it explodes in a burst of radiation and disappears. No more black hole. Just a few photons carrying away the last remnants of its mass. Once the black holes evaporate, there's nothing left. No stars, no planets, no black holes. Just photons, elementary particles, scattered across an expanding universe so large that the distance between any two particles is greater than the size of the observable universe today. The photons themselves will have been stretched by the expansion, red-shifted. Their wavelengths will be longer than galaxies, longer than the distance light can travel in 1 trillion years. They'll be so stretched, so diluted, that they effectively cease to exist as particles. The universe will contain energy technically, but it will be spread so thin, so evenly that nothing can be done with it. No work, no motion, no change. Just an infinite expanse of almost nothing, expanding forever, cooling forever, fading into a darkness so complete that even the concept of darkness stops making sense. That's the heat death, maximum entropy, thermodynamic equilibrium, a state where the universe has used up every possible energy gradient and has nothing left to do. No stars to form, no galaxies to collide, no black holes to evaporate, nothing. The universe doesn't end in a flash. It doesn't collapse or explode or rip apart. It just fades, quietly, slowly, into eternal silence. And here's the part that's genuinely disturbing. The heat death erases everything, not just the structures, not just the galaxies and stars and planets. The information, the history, every event that ever happened, every pattern that ever formed, every configuration of matter and energy that ever existed, all of it gets scrambled. Entropy increases, information is lost. In the heat death, there's no record of what came before, no fossil record, no ruins, no artifacts. The universe forgets, completely, permanently. The fact that galaxies once existed, that stars once burned, that life once emerged and looked up at the sky and wondered what it all meant, all of that gets erased, smoothed out, turned into a featureless expanse of thermal noise where nothing distinguishes one moment from the next or one place from another. It's not death in the usual sense. It's the absence of the possibility of anything ever happening again. Eternal stasis, infinite boredom. A universe where the laws of physics still hold, but nothing interesting is left for those laws to act on. The second law of thermodynamics, the one that says entropy always increases, wins completely. Entropy maxes out. The universe reaches its final state, and there's no coming back, no reset, no new beginning, just forever. The heat death is hiding in the empty space all around us right now. It's already here, in a sense. The voids, those enormous regions of almost nothing, are a preview of what the entire universe will eventually become. Stretch those voids across all of space and all of time. Remove the galaxies clinging to the edges. Wait a few 10 to the 100 years, and you've got the heat death. The universe is practicing, rehearsing its own ending. The voids are dress rehearsals for eternity, and the quantum ripples, the ones that started it all, will be long gone, erased, stretched beyond recognition. The cosmic microwave background, that faint glow encoding the seeds of structure, will have red shifted into photons with wavelengths longer than the observable universe. Undetectable, irrelevant. The evidence of the universe's quantum origin will vanish, leaving no trace that it ever existed. The beginning and the end meet in silence. Quantum fluctuations to cosmic nothing. A full circle from the smallest scales to the largest, from the briefest moments to the longest times, from something to almost nothing. But we're not there yet. Right now, the universe is young, middle-aged at most. Galaxies are still shining, stars are still forming, though slower than before. The cosmic microwave background is still detectable. The voids are still surrounded by structure. We live in the narrow window between the chaos of the early universe and the silence of the late universe. A brief era, cosmically speaking, when the universe is interesting, when things happen, when complexity exists. When entropy is high enough that structures have formed but low enough that those structures haven't all decayed yet, we're lucky. Lucky to exist in this window. Lucky to have eyes to see the stars and brains to wonder where they came from. Lucky to have instruments sensitive enough to detect the quantum ripples in the cosmic microwave background and telescopes powerful enough to map the voids and filaments and clusters scattered across billions of light years. We're living in the age of visibility, the age of evidence, the age when the universe is still willing to tell its story to anyone who knows how to listen. That story starts with quantum fluctuations, tiny, random, insignificant ripples in space-time that got stretched by inflation and grew under gravity into everything we see. It passes through the formation of galaxies, the ignition of stars, the birth of planets, the emergence of complexity and life and intelligence, and it ends in silence, in emptiness. In a cold, dark expanse where entropy has won, where structure has faded, where the universe has forgotten everything it ever was, from quantum ripples to cosmic silence, that's the arc, the full story, the beginning, the middle, and the end. And we're standing somewhere in the middle, looking backward at the ripples frozen in the microwave background, and forward at the voids expanding into the future, trying to make sense of both. Trying to understand how something as small as a quantum fluctuation could become something as large as a galaxy, and how something as vast and full as the universe we see today could eventually fade into nothing but darkness and silence. That's the reality. 95% of the universe is already invisible. Dark matter and dark energy holding everything together and tearing it apart, doing their work in silence while we scramble to figure out what they are. The visible 5%, the stars and galaxies and glowing nebulae, that's the exception, the anomaly, the brief, bright flash in an ocean of darkness that was there before we arrived and will be there long after we're gone. And in the end, the darkness wins, not because it's more powerful, but because it's more patient. Entropy always increases, energy always spreads out, structure always decays. The quantum ripples that built the universe will eventually be erased by the same expansion that made them cosmological in the first place. The voids will swallow the filaments, the horizon will shrink, the galaxies will vanish, the stars will die, the black holes will evaporate, and the universe will settle into its final state, a cold, silent expanse stretching across infinite space and infinite time, with nothing left to mark that anything ever happened at all. That's the echo of eternity, not a sound, not a signal, just silence, the final word in a story that started with a whisper of quantum noise and ends with nothing left to say. So where does that leave us? Standing on a rock orbiting a star inside a galaxy that's one of trillions, most of which have already vanished across a horizon we'll never cross. Surrounded by matter we can't see, pushed apart by energy we don't understand, living in a universe that's 95% invisible and getting emptier every second. The voids are growing, the galaxies are disappearing. The evidence is fading, and entropy, patient and relentless, is steering everything toward a silence so complete that even the memory of stars will be erased. That's not a comforting picture. It's not meant to be. The universe doesn't care about comfort. It cares about physics, and the physics says we're temporary. A brief window of complexity in a cosmos that started as quantum noise and will end as thermal equilibrium. Everything we see, everything we are, every thought you've ever had, every emotion you've ever felt, all of it is a statistical accident, a ripple in space-time that got lucky, that lasted long enough to become aware of itself before fading back into the void it came from. But here's the thing, we know. We figured it out. We looked at the sky with instruments that can detect light from galaxies billions of light years away, measured temperature fluctuations in the cosmic microwave background down to millionths of a degree, mapped the invisible scaffolding of dark matter holding everything together, and calculated the trajectory of a universe that's accelerating toward oblivion. We did that. A species of primates on a planet that didn't exist for the first 9 billion years of cosmic history looked up and decoded the structure of reality. That's not nothing, that's everything. The universe might be mostly empty, but the 5% that isn't produced something capable of understanding